السلام عليكم.
عليكم السلام ورحمة الله وبركاته.
أهلا دكتور عنتر.
أهلين، مساكم الله بالخير.
كيف حالك؟
الحمد لله بخير، الحمد لله.
We really need your support, Dr. Antar, to upload the slides like at least a day before the lecture so that we can print it out for taking notes on the slides. So
Yeah, actually, yes. Part of it is moving from one week to the other. So the base material will be there. I only updated one file today that has like an example that we're going to go through together. So I think on Thursday I put some material in, and I just updated it today. And I made some sort of an organization to the to the blackboard.
okay, because we print out the lecture, and if some changes occur, then it will be difficult for us to follow.
Yes. Yeah. The problem is that sometimes I prepare the material, and then while reading it in the night before, I just find that I need to make some changes. So that's an issue. You might do that, but maybe the one that you have will not be the last or final version, but the additions will be something which is not much, moderate, or mild, I can say.
Okay, thank you very much.
Yeah, okay, but I'll make sure that, I mean, and even pass the message to all colleagues who are going to join me in the next weeks that they will do that, something like by Wednesday or maximum Thursday to have their presentations posted.
Great. Thank you, Doctor.
You're welcome. So now I can see we became almost, so we have still 6 persons to join, but it's already 12:45, so probably it's time to get started. There are some communication items. I would probably wait a little bit until everyone is here, and then we can just share it amongst all of us.
دكتور
اتفضل.
السلام عليكم. دكتور احنا كنا نتناقش if you can make another help session as you did in the last week.
I'm not sure I heard you well. The voice is a little bit low, but I thought that you are talking about something related to a help session or so.
Yeah,
yes.
as last week.
Yeah, actually, we can do it same time on Tuesday, and this is a help session that I need to set it up and get it, share with you the link. There is another venue where you can, I can just put like a daily office hour, and then if somebody is interested to discuss something or have a question, he can join me in. The course, the university has created a Microsoft Teams link for this course.
Yes, Doctor.
The good thing about the Microsoft Teams is that you can log in at any time. You can post a question, and you can even ring me if I'm available. I will respond immediately. And then I'm going to post like at least other than Tuesday, 3 more times that you can find me in for an hour or so. We can call it an office hour or so. So I'm going to do that also.
Yeah, yeah, doctor. But in fact, we need like as a recitation or enhancement. We need some solving questions or something like practical.
Okay, that will be on Tuesday, inshallah. So like I did last time, but this time probably, or this week, we can select a problem and then we can go through the solution step by step. Actually, I was planning to do the same today in a problem that has as many components of a real power plant as possible. Maybe the number will not be exactly matching the same, but the principles are there.
Good, doctor. Thank you. We appreciate it.
You're welcome, sir. No problem. Now we're about 19, 3 more to join us. So let's at least get started with this intro. And then whenever they join, we can just share some communication. So currently, actually, it's not really currently. This is something like a 4 years ago sort of information that the energy consumption worldwide is about 12 terawatts. Emissions of energy has been escalating in the last few decades. And then the issue of talking about decarbonization, reducing of carbon dioxide emissions, through the switch to low carbon fuels has been something that that the call for it has been there, and now it's being I can say increasing in an exponential manner. People going from coal to oil to gas, that's what as fuel for the power plants. This is what the authors are considering as a wrong direction. Actually, what they are pointing here is that we better go into the renewables rather than just keeping with fossil fuel. And I think that this is something that even through the vision 2030 for the kingdom, that's something that we're moving into. The kind of electric power generation by solar energy is something that has been written, iterated, but it's confirmed that this kind of shift is expected in the near future. We're talking about a decade or less. Capturing and sequestration of carbon dioxide is required as long as the fossil fuels are going to be used. So going for low carbon fuels in addition to capturing and sequestration of carbon dioxide. So the point is, it is important to reduce the dependence on the fuel that produces carbon as much as possible in the near future. Probably you must have read through the news that some countries in Europe have decided that they are going to go for electric cars 100% in year 2035 or 2040, less or more, it depends on the country, but there's some sort of a direction into that, into going for electric cars in future. So they are going to replace, maybe not 100% in the next few decades, but eventually that's something that would be expected. The production or dependence on gas, oil, and coal in several places in the world is given in a table here that will give us an idea of how much of this and that over there. Coal is being used heavily in some places like China, Russia, and the United States. And that's something I think which is definitely there are grades of coal. Some of them are cleaner than the others, but still that remains some sort of an issue related to the carbon emissions that are products of the combustion process. This is the primary energy production that was back in 2005. Hopefully with the next edition of the book, this figure is going to be updated. Reliance on crude oil, on coal and natural gas, which are so far the most dependable sort of sources of fuel that would be there. I would expect when this one is going to be applied, a certain percentage is going to be allocated to the solar energy utilization. And that's something that keeps on increasing day by day. I mean, every now and then we just get news about building the biggest world solar power plant. It was in Australia, something like a decade ago. Last year, a bigger one has been built in Morocco. So there is a motion into this direction of generating electricity. Thermal heat was the major part in the last probably couple of decades. Now people are considering more and more dependence on the PV, especially that the price of PV panels has dropped. I mean, the technology has been made available and the price dropped in the last decades to about 1/3 of its original price. So there is a continuous decrease in the price of the materials that depend on solar energy, so that the investment in solar energy is not becoming that significant as it used to be before. Still, it's on the high side, especially of the capital cost, but this cost is being reduced as people are moving from one technology to another one. Fossil fuel availability, cost, and carbon dioxide emissions is something that we are interested in, and this is being covered in the current chapter of the book that we are getting into, the stationary combustion system. The basic combustion cycles. We started last time talking about Rankine cycle. We'll continue today talking about Rankine cycle, probably give some sort of a detailed example of analyzing a problem, having Rankine cycle, and some improvements that have been introduced to the cycle to increase the performance in terms of efficiency and work done. And then next time, which will be 2 weeks from today, you're going to start considering another thermodynamic cycle, which is Brighton cycle. Brighton cycle is the basic cycle behind the operation of gas turbines. And you know that power production in the kingdom is being basically distributed between steam turbines, Rankine cycle, gas turbines, combinations of them. In some of them, like for example, the power plant, which is located in Jubail by Marafiq company, they have a combination. They have steam turbines and gas turbines together. So that the steam turbines over there are basically because they needed steam to operate desalination, water desalination units, and Brighton cycle to produce power. And it's some sort of a semi or a totally private company. So what they do, they are selling the electricity to SEC, they are selling water to SWCC or even National Water Company for distribution. And that's some sort of a privatization that, again, there is a direction into this mode currently. The advanced combustion systems is having a combination of both of them, like having a gas turbine cycle, and the gas turbine cycle actually is producing or it is rejecting a substantial amount of energy to the surrounding. This energy is taken to heat the steam in a bottom cycle, which is the Rankine cycle. So a combination of both cycles is something that you will be exposed to once you get to know what's the Brighton cycle, and then the combination of the combined cycles would be there. Cogeneration has some definitions that might change based on the application. For example, if we are interested in only electric power consumption, then cogeneration would mean that you have a gas turbine, which is running a generator, and then which is the top cycle. The bottom cycle will be a steam turbine that would run another generator, and then you are producing electricity. This is in one hand. On the other hand, the issue of cogeneration can be looked at is that you are satisfying two requirements by a system. Like I just mentioned an example of a combination of gas turbines and steam turbines, the steam and steam power plant. The steam power plant itself can generate electricity and can produce some heat for any utility. The utility could be a process heater or a thermal desalination plant or district heating or whatever. So you are making use of the energy which is added into the boiler to create steam, and that steam, part of it would be expanded in a turbine to produce power, and the rest can be extracted from the turbine or bleeded from the turbine so that you can use it for any other application, a process that needs steam. It could be a paper company, for example, a paper pulp, or it can be a desalination unit or a process heater or whatever.
Doctor, excuse me,
Yes.
what do you mean by Brighton cycle?
Brighton cycle, it's a thermodynamic cycle. You know, Rankine cycle is a cycle which is made up of 4 components. The 4 components are the pump, the boiler, the turbine, and the condenser. Brighton cycle, on the other hand, is a cycle that is made up of several components that include, again, compression of air, and then using what we call an external combustion system. So a combustor that is going to burn fuel using this air, and then this is going to result in a high increase in the heat content that you pass through a gas turbine, you expand it, and the gas turbine generates electricity. So this is basically an application of Brighton cycle, and this is the one that you are going to be exposed to in the next module, inshallah. Did I answer your question?
Yes, doctor, thank you.
Okay, fine. Back again, this is a Rankine cycle. We have been considering an example of this cycle last time, where basically what we did is that we have taken each component as a separate example that we did, and we analyzed it. And then after that, we saw what is, or how can we introduce the system's efficiency as a part in the components, like the pump, for example, considering what if the pump has associated entropy generation, so we come up with a pump efficiency, and the same thing applies for a turbine. So that's something that we have been looking, and this is the temperature entropy diagram that represents this cycle. The pump here, we have a process going from 1 to 2, which is this. It's compression of liquid water from state 1 to state 2. Here we assume it's an ideal Rankine cycle, so basically there's no increase in entropy here. Whereas point 2 up to 3, this is a constant pressure line. If you remember in the first class, we said that when you are heating water at atmospheric pressure or at a certain pressure, it goes through sensible heating first, and then after that, it goes through a constant temperature phase change. And after all of it has been converted from liquid to vapor, it goes through an increase in the temperature again. So all of this is occurring at a constant pressure. When you change the pressure, you are going to have a line similar to that, and a line similar to that, and so on. So here we have heat addition in the boiler that starts at state number 2, which is this, and it is the exit of the pump. It will get to the boiler where it will be heated to saturation condition, and then a change of phase will occur until it becomes saturated vapor, and then further it will be heated into superheated vapor at state number 3. So this is sensible, latent, and sensible again until state number 3. Then the power that is obtained from the power plant is obtained in the turbine, where we are moving basically from state number 3 through expansion to the low pressure of state number 4, which is the same pressure as 1. So 1 and 4 is the low pressure side of the cycle, whereas 2 and 3 are the high pressure side of the cycle. You go from 1 to 2 by compression, and you go from 3 to 4 by expansion, and expansion here is associated with steam turning the blades of the turbine, running the turbine at about RPM of something between, if I'm not mistaken, 3,000 to 6,000 RPMs. And after that, that is connected to a generator to generate electricity. The cycle that we have seen here is ideal in the case, or in the sense that, number 1, there's no entropy generation. So from 1 to 2, it's a vertical line. From 3 to 4, it's a vertical line. And also, look at the line between 1 and 4. It's a horizontal line. So assume that as condensation is occur in the condenser from state number 4 to state number 1, the fluid is passing in a heat exchanger and there's no loss of pressure. The same thing, when we are saying we are going from 2 to 3, we are assuming that we are following a constant pressure line. In reality, this is not the case, because each fluid passing in a pipe, it undergoes friction with the pipe material. Friction is going to reduce pressure. This is what we call the major pressure loss. It's not the only thing, but there are minor pressure losses as well, which is if you have a bend, if you have a U connection in the piping, these are called, if you have a valve, all of these are minor losses that result in loss of pressure. So an actual cycle is the one that you are going to see at the left. So that from 1 to 2, there is sort of a generation of entropy associated with compression. From 2 to 3, you see here the dashed line is the actual line because it's taken into consideration the issue of pressure reduction. So you reach at point number 3 here. From 3 to 4, it's not a vertical line down because there is an irreversibility generated in the turbine. There is an entropy generation that results in an increase in the entropy while expansion is occurring, and then you get to actual point 4, and then from 4 to 1 in the condenser again, there are minor losses and major losses that are reducing the pressure. So in reality, you would know that this is the case.
Doctor, can I have a question, please?
Pressure reduction we might not consider in our calculations, but at least in the back of our minds, we know that it is expected to be there. Someone has a question?
Yes. Doctor, does that mean, first of all, can we specify one state in a cycle that it will be, for example, adiabatic? For example, if you go back to just one slide, if you please.
I just need to make a little correction, if you allow me. Adiabatic is a process, not a state. Processes are the ones that are having something constant or something is equal to 0. But that is identified by 2 properties. Like state number 1 here, we have a certain pressure which is known, and we know it is saturated liquid, so the quality is 0. So these are 2 properties independent to identify the state. But going from 2 to 3, we assume it's a constant pressure process, isobaric process. Going from 4 to 1 is an isobaric, constant pressure, yet it's a constant temperature process.
So can we call it from 4 to 1, can we call it, since no heat is lost?
No, there is heat loss from 4 to 1. There is heat rejection to the cell. You see, there is a Q out here. This is what happens in the condenser. In order
the
to steam leaving the turbine and convert it into liquid to get into the pump, you need to reject heat out so that all of the vapor will be converted into liquid. And this is done in the condenser by bringing water from a lake or a river or a gulf, and then you can cool down the water, cool down the steam so that it condenses.
Okay, doctor, then why from 4 to 1, the temperature is constant? Because
it's a change of phase. What here is that at state number 4, you have vapor with high quality. Say that is 85–90% vapor, so it has only 10% of liquid, and the rest is vapor. So what is going to happen is that it's going to condense at a constant temperature until all the vapor is converted into liquid. If you further heat it, or if you further upsize the condenser in terms of surface area, you might not be ending at point number 1, but you might be ending somewhere down here. So you have subcooled liquid. But for simplicity, we just assume it is saturated.
Does the same apply, doctor, for example, when we have ideal cycle, heating will be at a temperature of 100. Does that mean, for example, water will be first transferred all from liquid state to vapor state, then it will be going to superheating?
Exactly. Actually, look at here the line taken from 2 to 3. And at this pressure, 2, we have subcooled liquid, which means it's a liquid below the saturation or the boiling temperature. So adding heat to it in the boiler is going to heat the water until it reaches the boiling temperature. When it reaches the boiling temperature, it's still being heated, but the heat will not result in temperature increase. Rather, it will be used to break the bonds between the molecules. Liquids are having molecules that attach to each other strongly. You need high energy to break this bond and separate them from each other, which actually means that you are converting it from liquid into vapor. So all the heat added between this point here on the saturated liquid line and this point in the saturated vapor line is not going to be increasing the temperature. It will be only breaking the bonds and evaporating the water, converting it from liquid water to vapor. When it's all vapor, additional heat is going to increase the temperature. So we have a part of sensible heating here in the compressed liquid region, in the superheated vapor region, and we have a constant temperature and pressure here in below this dome, which represents the place where you have a mixture of liquid and vapor are occurring.
Thank you, Cliff.
Doctor, I have a question here.
Go ahead.
Now the saturation that we have it from 2 to 3, we have steady state. Then we it's jumped to 3. Okay, then we go to 4. Okay, so
It's
now
all steady state, by the way. Everything is steady state here, which means that with time there's nothing changing.
okay.
You have a certain flow rate of the water going into the pump. This water, which is being pumped to higher pressure, is going to go to the boiler. It will be heated to saturation temperature, boiling temperature. It will start evaporating until it's all vapor. It will continue to superheat it. It will go to the turbine, expand to point number 4. It will condense to number 1, and then it will be repeated again. So that's some sort of a process which is repeated again and again and again and again with no changes over time. That's what we mean by steady.
Okay, how it will go for superheated? Is there any device or how
It
will go?
You have a
After
boiler.
the boiler?
You have a boiler and you are burning fuel. Say that you are burning diesel there or heavy.
Okay.
And this diesel have enough quantity of energy that it heats the water to saturation temperature, it evaporates the water, and it superheats the water to high pressure and temperature condition. Actually, the boiler itself, we are looking at it as a block. In reality, the boiler has several components. It has a main boiler, and it has a special kind of tubing on the top of the boiler called superheater. So this process is occurring inside the boiler, but it is occurring within the context of one device.
I get your point, yes.
Which is going to do that. Okay.
Doctor, excuse me.
Yes.
The phase between 2 and 3 with a constant pressure.
Yes.
Okay. Thank you.
Okay, you're welcome. So this is actually what happens. Our coverage of this part, we are going to neglect all of this this is tedious, and normally, practically speaking, people will not look at how much the pressure would be reduced within the boiler. I mean, practically speaking, you can put a pressure gauge at the inlet of the boiler and a pressure gauge at the exit of the boiler, and then it will tell you how the pressure drop is there. But you don't really go for calculating it unless you are designing the boiler, which is something basically we don't do. Maybe you can order a boiler, and then you can visit the company and you can get all the design sheets. Then you can look at the calculations that estimate how the pressure loss will be. But for our analysis, what we are interested in basically is going to be the kind of irreversibilities associated with compression and with expansion. But we are going always to assume that this is going to be sort of a constant pressure line. Now, coming to another issue of, if this is the Rankine cycle and you need to improve its performance, what can we do? Improving the performance means what? Means that we need to increase the work done and the efficiency keeping the heat input the same, which is what's being assumed in this figure. What we did here, we have gone from this line of expansion, instead of expanding from 3 to 4, we're expanding from 3 to 4 dash, which is a lower pressure. For example, this could be the atmospheric pressure, but you might need to expand the steam into a pressure of 10 kilopascal, which is typical in many of the desalination, the power plants, so that essentially the compressor is operating in vacuum condition. What did we do here? We increased this area, the shaded area that we have in the bottom. This has been added. The point of heat addition is the same here, but the area which is covered by 1 dash, 2 dash, 3 to 4 dash is becoming a larger area. This area represents the work done. So what we did here, we have increased the work done. And when you look at the efficiency, it is nothing but the work over the heat addition. The heat addition is the area under this point from 2 dash to 3 down until the bottom. So that's something that can work out in increasing or lowering the condenser pressure, is an effective way to improve the system performance. Another way is to superheat the vapor further. And instead of superheating it to state number 3 or superheating it to state number 4. Again, this is going to increase the work net, but this is coming with a different price, which is increasing the fuel added in the boiler, maybe upsizing the boiler, and then this is the price that you are going to pay to increase the work. And the price that has been paid in the previous one is to guarantee that you are going to have a vacuum system that's going to expand the steam in the turbine to very low pressure. And you are going to maintain that under vacuum and make sure there's no leakage to the surroundings. So some sort of a more robust design of the contacts that are related to the pipes and the condenser. And these are things that are to be looked at. Another way to improve the performance could be by increasing the pressure itself of the boiler. So instead of the boiler going to the pressure line from 2 to 3, you decided to go from 2 dash to 3 dash. Let's see what are the consequences. When you are going to do that, definitely higher pressure is going again to require that you might be adding higher, definitely the pump here should be bigger pump to bring the pressure from 1 to 2 dash rather than from 1 to 2. And then going from 2 dash to 3 dash, which is to the left of 3, because this is the line of a constant pressure. So you are going to increase part of the work here, and then there's a decrease in the work here. So the net value, is it going to be a decrease or decrease? There's no one answer. It needs to be analyzed to see, are we going to get a benefit of increasing the pressure or not? You might still do that, but I mean, overcome this decrease by increasing the value of 3 dash, the maximum temperature, to a higher value, but this is going to need substantial amount of fuel. So you are increasing work, and meanwhile you are increasing Q. So what about the efficiency? It may or may not increase. Or maybe going for what is called a supercritical cycle, in which you are increasing the pressure here to a value beyond the critical pressure of H2O or water, and hence you are basically going over above critical point and reach to state number 3, and then you are going to have a substantial increase in the work done. But Q is going to increase as well, so that's some, and the power of the pump which is needed here. So again, that's something needs to be looked at. How much is the benefit that we are going to get out of doing that? So we're talking basically about 4 types of processes that we can do to improve work done, efficiency of the cycle, decreasing the pressure of the condenser, increasing the degree of superheat and increasing the pressure of the boiler, or even going for a supercritical Rankine cycle. But these are not the only ones. There are other ways that you can do for an existing unit to get the performance better without having to increase or decrease pressures. These are basically some sort of a comparison that's considering 3 of the 4 scenarios that we talked about. One of them is by what we're doing here is an original state of a cycle in which the low pressure is 10 kilopascal, the high pressure is 3 megapascal, and you are superheating the steam up to 350 centigrade, and then it will expand here up to state number 4, where we have a quality of the vapor of 81%. Efficiency of this system is 33.4%. Whereas if we increase the degree of superheat, instead of superheating from 3, we made the superheat up to 350, it is expanded to 600 degrees centigrade, then definitely we have more Q added, but we are getting a couple of benefits. One of them is that we have higher work and the efficiency of the system increased, which is 37.3 here. But we have another benefit, which is state number 4. Compare the leftmost curve with the curve, figure with the figure in the middle. You'll find that in the middle, the 0.4 has moved to the right, which means what? Which means that the quality of steam, which is leaving the turbine, is better, less water content. And in the turbine, actually, we need to avoid water content as much as possible. If we have a way that the vapor which is leaving the turbine is leaving slightly to the right of this point, maybe here as a superheated one, that's going to guarantee longer life for the turbine. So that's something, again, we need to avoid as much as possible having water or moisture content in the turbine. Otherwise, special materials, special coating so that corrosion would not occur. This is compared with the rightmost figure here, where we are talking about very high pressure, which is 15 megapascal compared to the 3 megapascal. The efficiency has increased substantially, but look at the value of the quality. Because at higher pressure, it is getting narrower. The pressure lines are getting narrower. For the 600 degrees centigrade, we have moved a little bit to the left, and that has brought a substantial amount of moisture content in the vapor leaving the turbine. There's a solution for that. And the solution can be done in a process that we call reheating of steam. And this is basically what we need to talk about now. That you might bring or divide the expansion in the turbine into 2 processes. So you have a high pressure turbine and you have a low pressure turbine. In the sense that whatever the steam that is expanded in the high pressure turbine is taken back again to the boiler. So you reheat it. That's why it's called ideal reheat Rankine cycle. You reheat the steam which is leaving here, and then you admit it to a low pressure turbine. Look at the curve. What did we do here? This is compression by the pump from 1 to 2, and then going through the boiler from state number 2 to state number 3. At state number 3, you are extracting all the steam from the high pressure turbine, and you are sending it back again. It has expanded from 3 to 4, and at point number 4, you are taking that steam, all of it, and you are sending it back again to the boiler to be reheated to the same maximum temperature. And then when you expand in the turbine, definitely you are far away, or as close to the saturated vapor condition. If we maybe consider the efficiency of the turbine, it will take us into the superheated version, superheated region, which means that we have protected the turbine, we have increased the work substantially, we have adding all this area to the right here to the work done. And definitely the Q, the heat transfer rate, increase a little bit, but the potential benefit in terms of addition of work and quality of steam which is leaving the turbine is substantial. So almost every power plant working on Rankine cycle right now is having this kind of reheat in the boiler. Is that the only way that we can get this benefit? Actually, no. There's another, or there's something else that we can do to increase the cycle efficiency, which is, look at here, point 1 to point 2 is the compression in the pump, and point 2 is the point of inlet to the boiler. And then going from point 2 to 3 to 4 to 5. 3 to 4 to 5 are somehow in the high temperature zone. You can see that. But looking at the overall temperature within the boiler, average temperature, it would be somewhere here, because this value is low and these values are high. So the question was, is there a way that we increase the average value of temperature inside the boiler? Or in other words, can we preheat the water before it enters to the boiler so that the entering point to the boiler, instead of coming at this low temperature side, it can be somewhere here? Can we do something to preheat the water before admission to the boiler? And if we are able to do that, then this is a benefit because you are going to reduce the kind of energy added by fuel in the boiler. The answer, yes, it can be done, but nothing is coming free of charge. There must be a price that we have to do. And the price is, if we take a line of steam from the turbine and use that steam to preheat the water, we're losing something. We're losing a part of the expansion to power. So a little part of the power is being affected. But meanwhile, the kind of extraction that you have taken from here in a heat exchanger is going to preheat the feed water before it is admitted to the boiler. And that's why you add a device here that we call feed water heater. What is going to do? It is going to increase the temperature of the water which is entering into the boiler in this Rankine cycle. Now, do you remember what was the Rankine cycle, ideal shape of the Rankine cycle that we talked about? It was basically something close to the Carnot cycle. To remind you, Carnot cycle has constant temperature heat addition, constant temperature heat rejection, and then isentropic compression and isentropic expansion, which means that the temperature addition was occurring at a constant value. Can we reach for a constant value here, or at least an average value which is quite high, close to the upper limit? Yes, theoretically speaking, and only theoretically speaking, yes, that can occur if we have infinite number of feed water heaters. That's something that we do on paper, but in the plant, there's nothing called infinite. There must be some sort of a number to put there. How many feed water heaters should we use so that we can preheat the water enough before it enters into the boiler for evaporation and then superheating? So the ideal thing is take this amount of water and introduce it to the boiler while it is saturated water or close, so that you don't spend energy in physically or sensibly heating the water saturation condition, but you just take it as saturated vapor, and every energy added in the boiler would be there for evaporation. This looks like a theoretical thing, or just imagining ideally what would happen. In reality, that does not occur, but what we can do, we can approach as high temperature as possible for the inlet to the boiler. And this is going to be done by using more than one feed water heater. So this is the idea of regeneration. So the water that enters the boiler is going to the boiler at a low temperature. It's heated to the maximum cycle temperature. So we're talking about an average temperature which is somehow low. We need to increase it, because increasing it is going to get us close to the idea of the Carnot cycle. This can be done by reheating, but it's not enough, but it can also be done by regeneration, so that we bleed or extract a portion of the steam in the turbine, and we use that for preheating the feed water, which is going to feed the boiler. And that's why it's called feed water heater. So the device in which heat is added to the feed water is called feed water heater. Regeneration has been found useful in processes other than just heating the water. In the condenser, which is at a low pressure process, condensation can be accompanied by having, vapor will condense. As it condenses with a possibility of creation of non-removable, non-condensable gases. Air can leak into the condenser, having the condenser operating at a very low pressure. So air might leak inside. We don't want air to be admitted to the boiler at all, because it is going to, with a high temperature in the boiler and air, oxidation would occur and result in corrosion. So that's something that we need to avoid, meaning that we need to remove air from the water that will go into the boiler. This is a process called de-airing water or deaerating water before getting into the boiler. One of the feed water heaters is an open type feed water heaters, and it is working as a deaerator at the same time. So you are preheating the water in a preheater. Meanwhile, you are taking out air from this stream, and that enhances the performance of the whole system or the whole cycle. So that's an open water heater, which is nothing in chamber. Someone had a question?
Yes.
Go ahead.
So you are saying that we will be using a deaerator only and only if we have a feed water heater. Is that correct?
Actually, what I want to say that a feed water heater is a deaerator at the same time. The feed water heaters are two types. One type of them is open and the other type is closed. So if you are going to have a power plant, then we might need only one open feed water heater and 3 to 4 up to 7, practically speaking, closed feed water heaters. So we need only one feed water heater that is open to work as a deaerator, and the rest are going to be basically closed feed water heaters. So what I want to say is most, or actually all of the plants, the modern plants that we have and they are operating, they used to have feed water heaters. That's something which is a standard to the technology now, because that's a tool to improve the performance. But
so, Doctor,
since we need a deaerator, one of them is going to be an open feed water heater.
Can we say that a deaerator is simply, it's like a fan that will absorb vapor from water going back to the phase 1 of the cycle?
You can say, to be more closer to the equipment that we are dealing with, you can say that it's a feed water heater. It's a mixing chamber. Because you are going to kill two birds with one stone. One of them, get rid of the gases. Second, preheat the water. So it's a mixing chamber.
But Doctor, I'm talking from industrial point of view. We take care a lot about the cost, and if only we are doing this feed water heaters, we are using them to make sure we can raise the temperature before it gets into the saturated mixture, right?
Oh, yes.
Yes. So if we are going to pay more for feed water heaters, but less, or let me say, a very small amount of the the efficiency of the cycle itself will be increased. Do you think that this is a good idea to use for feed water heaters or not? Or simply, when can we use them efficiently?
Actually, the answer to your question is a practical answer to the power plants that exist. Not all of them are having feed water heaters, which means that using the feed water heater to preheat the water and accordingly reduce the fuel quantity that goes to the boiler has proved itself as a reliable technology. And that's why you have that. As I mentioned, practically speaking, or let me bring it in, ideally speaking or theoretically speaking, you may need infinite number of feed water heaters, but that will not make sense economically. So you are going to add feed water heaters as long as you are going to benefit from increase of the water in improving the efficiency. Until the point that adding one more feed water heater is not going to be useful, then you stop it there. So the point is, how many feed water heaters? How many? That depends on the economics. But do we have to have feed water heaters? Yes, the answer is yes, because it has a good effect on improving the performance of the system. And by the way, increasing the efficiency by 1%, even 0.5%, is a substantial achievement. And we will see in an example here that using feed water, a couple of feed water heaters, or maybe 3, can have an improvement in the efficiency about 3%, which is significant kind of addition to the current technology. So this is a partial answer to your question. It will continue whenever we go through a numeric example, and then you can see how the efficiency can be affected by adding a feed water heater.
Thank you.
So what we do, we take a fraction of the water from the turbine, fraction Y, a certain percentage, you extract it, you pass it to the feed water heater, and the rest of the water, which is 1 minus Y into the flow rate, expands to the condenser pressure and produces power. The cycle efficiency increases using a certain number of feed water heaters. The modern plants that exist so far, they have as many as 7 feed water heaters, as 8 feed water heaters. 7 of them are closed type feed water heaters, and 1 is an open type that works as a diaerator. The optimum number depends on the economics. Prices of the feed water heaters, prices of the fuel are going to determine how many that you want. A feed water heater in one way or another is nothing but a heat exchanger. And this is some sort of a very well-known, proven technology. And as a matter of fact, because steam is being used and we are having a combination of steam and condensed water, which are basically clean. So maintenance of the feed water heaters is not a big deal. I mean, I've been chatting with one of the engineers in Ghazlan power plant, and he was saying that they do maintenance for the feed water heaters every number of years. So that's something that you don't have to do frequently, because basically what you have is pure water and steam.
Excuse me, Doctor.
Yes.
What is the main difference between a feed water heater and deaerator?
An open feed water heater is doing the same thing as a deaerator means. So a deaerator can be looked at as an open feed water heater.
Okay.
But not all feed water heaters can work as deaerators, only the open ones. Closed feed water heaters are not.
So the main purpose from feed water heater is to increase the temperature up to saturation point.
We cannot reach saturation point, but we can increase
close to saturation.
Economically, yes. And another purpose of the feed water heater, that if it's an open feed water heater, then it also gets rid of the oxygen which is carried by the water.
Okay, thank you.
What we see here is a case where we have a power plant with one feed water heater. It's an open type. And what we are doing here, let's look at the cycle itself. We are going through, the sketch of the cycle, which is to the left. Saturated liquid going to the pump. It will be pumped to a higher pressure, which is compressed liquid. And then it will enter into the feed water heater. It will mix with a line of steam extracted or bleeding from the turbine. So this line of steam is going to operate in heating this stream of the water. The mixture of them which actually, because this is steam coming in and this is water, steam going to condense into liquid, giving off its energy to that stream of water, so that the stream of saturated liquid is going to leave here at a higher temperature. It will enter to the second pump, where it will be pumped to state number 4, and then it will be the whole stream is going to go to the boiler for heating, superheating, and then it will expand in the turbine at an intermediate pressure. This part of the extraction is going to occur. The rest will expand. So Y will be extracted. The rest, which is 1 minus Y, is going to expand to condense in the condenser and then go to the pump number 1, and the cycle repeats. When you look at the right, from 1 to 2, this is what's happening in the pump, first pump. And then from 2 to 3, this is basically sensible heating of the water from compressed liquid to saturated liquid at state number 3. How this addition has been going from 2 to 3 is by the heat added here, by that line of steam, which is Y. At state number 3, we are increasing the pressure and slightly the temperature of the water from 3 to 4. So that we go from pressure at 3 to pressure at 4. Now this is the inlet condition to the boiler. Before it was 2, now it became 4. So this is a substantial increase in the water, in the heat content of the water that enters into the boiler. A little bit of sensible heating and then latent heat and superheating. And then in the turbine, you expand from 5 to 6. At number 6, there is a stream Y or fraction Y, which is being extracted here to get into the feed water heater, and the rest, which is 1 minus Y, is going to expand from 6 to 7. So this is basically how the system looks schematically and on a temperature entropy diagram. Values, heat addition is basically from 4 to 5. Expansion actually is being done in 2 parts. Work of the turbine, all the steam has been there to be expanding from 5 to 6. So H5 minus H6, and then we have taken part of the steam, the rest, which is 1 minus Y, is going to expand from 6 to 7. So when you look at the work of the turbine, it's H5 minus H6, in addition to fraction of the mass flow rate, which is expanding from 6 to 7. The pump works, actually, this pump, or pump number 1, whatever is going into pump number 1 is 1 minus Y. So 1 minus Y is going to expand, to compress from 1 to 2. And then this open feed water heater, which is very much the same like a mixing chamber, we are mixing the 2 streams, Y plus 1 minus Y, and then the total is going to pass into pump number 2.
Doctor.
Accordingly, pump number 2 basically will be having the whole stream of steam moving in.
دكتور
Yes.
ليش ما يكون عندنا only one pump اللي هي pump number 2 ما نحتاج pump number 1?
Because it's an open feed water heater, and for an open feed water heater you need another pump. Look at the point that we need to reach here. You can have one pump that will take us from 1 to 4, but point 4 is going to be somewhere here. But need 4 to be at a higher value of the temperature.
But can I have only one pump between 3 and 4? يعني after the feed water heater?
After the feed water heater, yes, there is one pump, but you have to have a pump before it, which is from 1 to 2, so that you can go. Look, when you have an open feed, when you have a mixing chamber like that, you have to make sure that the pressure of the 2 streams coming in is the same pressure. Otherwise, the steam is going to come from here and then go on the other side. So they have to be basically at the same pressure. So points 2 and point 6 should be at the same pressure. Otherwise, the flow is going to go in this direction or in that direction.
Okay.
This is another system where you have a closed feed water heater and a mixing chamber. or an open feed water heater?
Doctor, if you don't mind, I have a question.
Yes, go ahead.
Can you just go back for the previous slide?
Yes.
So now to calculate the WP, which is the work of pump, I think this is the total, isn't it? We said 1 minus Y multiplied
which
by,
is
yes.
Work of pump 1. The pump that we are calculating here, this is basically the total or the work of the pump based on 1 kilogram per second of steam passing. But the 1 kilogram per second is not passing everywhere. You have 1 kilogram per second passing in number 4, in 5, and then here a fraction is going to be separated to go for 6 for the feed water heater. Say that this fraction is 10%. So 10% in the steam has gone in this direction, while 90% has expanded here. And the 90% has passed by the condenser. And the 90% has passed by the pump. And then the 90% is going to gather with the 10%, and then the 100% will go through per pump 2. That's why you have the 1 minus Y here.
Okay, what about down? Y equal M6 over M5?
Yes, that's basically what is Y. What is M6? At number 6 here, this is the Y, isn't it? The fraction. And in 5, we have the total quantity of steam. So the mass flow rate at 6 is only fraction, which is Y. That's why Y is 6 over M6 over M5.
Sorry, what's the mean of M?
It's the mass flow rate.
Mass flow rate, okay.
Mass flow rate of steam, yes.
Excuse me, doctor.
Yes.
What's the difference between open feed water heaters and the closed one?
What is it? Again, your question?
Yeah, what is the difference between the open and the closed SWH?
Yes, this is an open feed water heater where this stream of water is mixing with this steam, and the steam will condense in the water, and all of them are going to go through state number 3. So 2 streams are being mixed together.
Mm-hmm.
This is an open feed water heater, okay?
Yeah.
What about a closed feed water heater? Look at this, they are not mixed. Whatever is leaving at state number 2 here is going to get inside the pipes until it reaches to state number 9. But whatever is coming from 7, it's going to condense on the outer surface of the tubes, and the condensate will go to state number 3. So that is what you see typically in heat exchangers. You have a tube side and you have a shell side. The tube side is going to have liquid water that's going to be pumped here. This liquid water is going to receive energy from the steam, and the steam will condense on the outer side of the surfaces, and then the condensate will be pumped here to the next one. So here they are not mixed with each other.
أعرف يا أبو حسين إني مشغل النت عندي على المحاضرة على الجوال.
Abdurrahman, I think you, okay, fine. You already muted. Okay, so is the difference clear? An open water heater, we mix the fluids, but not in the closed feed water heater.
That's clear.
Now,
Doctor, what's the point of having both?
You don't need a mixing chamber for all of them. There's no point of having it. I mean, a typical heat exchanger, which is closed one, is easier to operate. It is smaller in size, and I think the cost is less as well. So that's why you have closed feed water heaters there.
So which one would be in the tube, the feed water?
Both of them are feed water heaters, but the one to the right is closed feed water heater. The one to the left, which is a mixing chamber, is an open feed water heater.
Yeah, I mean in the closed feed water heater, which the steam will be on the shell side?
The steam will be on always steam is on the shell side.
Okay.
It is coming from the turbine, and it just condenses in the shell side on the outer surface of the tubes. Now let's look at the process here. From 1 to 2, we have pumping in a pump. and then which is this, from 1 to 2, and then from 2, the line is taking us to state number 9. So then from 2 to 9, which is this, and then in 9, there is mixing between the streams. 9 is liquid, 4 is liquid, and 5 is liquid. So all these liquids are mixed together in, and all of them are at the same pressure. So 9, 5, and 4. Inlet is 9, which is at a lower energy, lower temperature. 4 is at a higher temperature, and then the resultant is somewhere in between the temperatures. That's why here 0.5, which is the outlet, is somewhere between 4 and 9. And then from 5, the fluid enters to the boiler, where it will be heated and superheated to state number 6. There's expansion to state number 7, where an extraction Y of the steam is going to be extracted to enter to the feed water heater. The rest, 1 minus Y, is going to expand to the condenser pressure. It will be pressurized to state number 2, and then it will continue. Then whatever we extracted from number 7 here is going to be condensed here, given the heat to the water in the closed feed water heater, and then it will be pumped back again to the high pressure of the turbine. This is intermediate pressure at 7, and 4 is the high pressure of the turbine. 7 and 3 are at the same pressure. You can see this line here, 7 and 3, and the pump is going to pressurize it to pressure number 4, which is the pressure of the boiler. Pressure 4, 5, and 9 are the same.
Doctor, can you explain again 9, 5, and 4?
Between, actually, 5, 4, and 9, this is basically the inlet and outlet from an open feed water heater or a mixing chamber. It must be that the 3 streams would be at the same pressure. State number 2 is at the boiler pressure. State number 9 is at the boiler pressure. We said that we are going to neglect the pressure losses in pipes. But state number 7, which is being extracted midway in the turbine, this is a pressure lower than the boiler pressure. The boiler pressure is this line, whereas the feed water pressure is in this line. So at 7 here, this is a low pressure compared to the 6, and then it is going to lose some energy by condensation from 7 to 3. So 3 is saturated liquid at pressure P3. We need to bring it to pressure P4 before we mix it in the mixing chamber. That's why we have this pump. So you pump it to the high pressure, boiler pressure, and then the 3 are in the same pressure. So mixing is going to occur, and then you have inlet to the boiler.
دكتور محمد.
تفضل.
يزيد فضلك. I just want to check my understanding.
Go ahead.
This whole cycle we have here is the purpose of it is to generate power after going in the turbine, right?
Is to generate energy, yes.
Yes. Okay. And after the reboiler will take this fluid and make it steam, then it will enter the turbine.
The boiler is going to convert the fluid which is entered from state number 5 as liquid water. It will convert it into superheated steam at 6.
Okay, then the superheated steam will enter the turbine, then we'll have this energy.
Exactly. Part of it will be extracted halfway in the turbine, and the rest is going to continue expansion until the bottom pressure, which is pressure 8.
And what's taken in the midpoint, we will return it from steam to fluid again.
Exactly. It's steam. We are going to condense it in the feed water heater, and then we're going to mix it with the other stream so that the whole water flow rate is going to enter to the boiler. What is the reason of this additional portion, which is there in the middle, is just to bring the temperature or the inlet of water going to the boiler from this state to that state. This is what we are looking for.
Doctor, what does sublet?
When we have this one, when we have it entering the boiler at a higher temperature, we'll have less work done on the boiler to get the steam, right?
Yeah, less energy added in the boiler, to get steam, and accordingly, when QA gets a little bit less, then the efficiency of the system increases.
Doctor, what does sublet step 7 about this step 8?
Actually, as a matter of fact, this figure is oversimplified, but this figure probably it would be redrawn if we split the turbine to 2 turbines, so that we have high pressure turbine and low pressure turbine. And this is basically what happens.
Okay.
Actually, you have a high pressure turbine, intermediate pressure turbine, low pressure turbine, or high pressure turbine, intermediate pressure turbine 1, intermediate pressure turbine 2, intermediate pressure turbine 3, and low pressure turbine. So basically, it's not a one turbine, but it's more than one turbine there. And expansion is going from one to the other depending on the points of extraction that you want. Like this. Actually, as a matter of fact, this should have been drawn as 1, 2, 3, 4 turbines, for example. And this is typically what you can see in a problem dealing with power plants. You can see here that we have 4 feed water heaters. 3 of them are closed, 1 is open for deaeration, and the others are there. And in addition, there is something which is called steam trap at the bottom. The steam trap here has a purpose. If not all the vapor or the steam that came here, if not all of it has been condensed, then it is going to get back again and join the previous one. And this is an issue. We don't need steam to be there. So we trap the steam so that whatever is going to go to the next stage, whatever is going to be pumped, it should be only water. So the trap here is there to reduce, or actually to eliminate any steam coming from the unit and going forward. So typically, you can see this as a typical problem dealing with a power plant. When you look at the actual chart of a power plant, you can find that they have maybe twice as much feed water heaters as they are here, but the idea remains the same. We have all of steam is going here. You have an extraction Y here to this closed feed water heater, another extraction Z here, another extraction W here, another extraction U here, and the rest is going to condense here from this to the condenser pressure. If you are collecting the steam in the traps, whatever steam is here, if there is steam, you take it here. And then if steam here, they are collected all together to this feed water heater. If it is, until you get rid of it all, you get rid of the gases. And here the condensation is going to continue. And then all the liquid is being taken to the boiler. If there is steam to be trapped from the first closed feed water heater, you return it back again to the condenser so that it will condense there and you have all condensed water. The point here is not you are losing any kilogram per second, but it's a closed system in a way that steam is not escaping in the form of either vapor or water from the system.
Victor, what does trap do?
The trap is getting rid of the steam. Actually, it passes only the steam. It does not pass the water out. Sorry, I mean, it's, when you look at, let's follow this, let me get another pointer so that we can follow the stream which is moving here. So, yes. So that stream of water is coming here. It should condense here. The condensate is going to have a mixture between, basically it should all of it be liquid, which is passing here. If you have vapor, then vapor is going to be trapped here.
Victor, we cannot see the...
Could be for vapor or could be for non-condensable gases. Like, for example, if in the steam is coming with a little bit of a non-condensate, which are, if you have some impurities in the water or something that's going when it condenses, generates gases, you can get rid of the gases here. So only the liquid is allowed to get into this. Okay. So the point is, what we need to admit to this part should only be liquids, and we should not get gases in. If gases are there, then you put a trap and get rid of them. Practically speaking, there are ways that you can get rid of the gases. In some plants or in some systems, they use something that's called ejectors, and the ejectors are there just to vent out the gases which are not needed. The system itself, in this system, we do not really have, we don't have a feed water heater in the sense, but we have something that we call a process heater. The system that we have here might not a very efficient one, but it is one of the examples that could be there. There is a feed water heater, which is open type, only one, but there is a process here. There is some sort of device which is located here in this unit, which is this. Suppose that you have a power plant which is located in a chemical plant, and you need heat, for example, for a distillation column. You should not get a separate source of heat, but you can extract a line of some steam coming from the turbine, and that produces the heat required for your process. So the process here could be a process heater, it could be a desalination system, it could be whatever. But the point here is that you need some heat to be obtained from that whole operation, and then you operate something else in addition to the to producing power from the power plant. And this is typically found in desalination systems where you have a Rankine cycle. You take a line of steam from the turbine and you admit it to something that we call the brine heater, so that you heat the seawater to a top temperature of about 120 degrees or 115 degrees, and then you take this hot seawater and you convert it into liquid, into fresh water. You needed energy there, and the energy is basically obtained from a power plant. This is a typical drawing. You'll find it in your in the book, which is basically for an ideal reheat system in a combined power plant in Cornell in the US. And actually it has steam which is obtained from the steam turbine. You can see it is, or a part of it is being extracted from the steam turbine, and it's going to the campus for reheating. It's called low pressure steam, which is basically here. So you are extracting steam from a turbine, from a low pressure turbine, and this is passing in pipes there. Probably it would go there for heating, district heating of the buildings there. It's called city, and then it needs heating. Then it will condense there, given off the latent heat for heating purposes in the buildings, and then the condensate is going back again here to join in the, it will enter as a liquid into the generator, into the steam generator or the boiler, or maybe it can join the condenser depending on what is the pressure of that. What we have here basically is a combination. There is a steam power plant, so there is a turbine, a boiler, steam generator, which is basically here, a boiler, and then the turbine is here, the steam turbine is here, and then the electric generator is located here. But this is not the only system that we have, but there is air coming in this part. Air is being introduced into a condenser, and then, into a compressor where it's being compressed to the combustion chamber, and then the combustion chamber is producing high enthalpy flow that goes into a gas turbine. The gas turbine is connected to a generator to generate electricity, and the exhaust of the gas turbine, which is very hot, is going here to be the source of energy in the steam generator. So we're talking about a cogeneration plant or a combined plant which is producing energy through a gas turbine system, which is this unit at the left of the figure, which is this part, a gas turbine. It has a Rankine cycle, so that we have a boiler and a condenser here, and some of the stream which is expanding in the turbine is taken for heating purposes as well.
Doctor?
Yes.
Yeah, I think this type of classes really require us to have full attention. So it will be healthy for our understanding to have more frequent breaks, like every hour or hour or 15 minutes, for us to refresh and come back to
That's fine. Now I've been like 1 hour and 15 minutes.
Yeah.
Okay, fine. So actually what we are going to do now is go through a numerical example. So it's a good idea to stop here. I mean, responding to your request. And here we can stop like for 10 minutes, get yourself a bit of refresh, get some tea or coffee so that we can go through some calculations together when you get back. Now in front of me, it's 2:03. So shall we go back like 2:15 will be okay?
Yeah.
Yes.
Okay. Then hopefully we'll go for about 1 hour, 15 minutes or a little bit less. And then we'll take another short break of 5 minutes, and then we'll get the third part of the class.
Okay, thank you, Doctor.
Okay, welcome. So we'll be back by 2:15, inshallah. Okay, Assalamu alaikum. I just wonder who is back with us and who is not yet. So can you please click on the yes, which is the button, yes, the green one at the bottom. At least we would know how many are with us so far.
No icon, yes, yeah, Doctor.
Excuse me?
You said to press yes. What do you mean by yes?
If you press on the link of participants, you have a list of names shown, and down there is yes, no,
Yes.
slow, go fast. So yes is what I'm asking for. Could you see it?
Already.
So far I just see 16. So 17 now. So we have 18. Okay. For those who have just probably joined us now, I just asked you to press on the check mark yes at the bottom of the participants list. I just see who has joined us. So far, we don't have Basil. Not yet joined. And Mu'taz al-Qahtani, not yet.
Yes. Yes, yes, this is Basil.
Oh, Basil, okay, fine. So can you just click on this, Basil, that yes check, which is at the bottom of the participants' names?
Okay.
Thank you. And Mu'taz al-Qahtani is not yet joined us. And Muhammad Mutlaq al-Utaybi. He has not yet joined.
Yes, معتز القحطاني, Doctor.
Oh, Mu'taz, you are here. So would you please just check this yes sign, which is down there, Mu'taz?
Yes.
There is a below the participant name, there is a green yes check. Can you just click on it?
Yeah.
Yes, okay, thank you. And Basim bin Awain. So we'll have two still to join us. Muhammad al-Utaybi, Muhammad Mutlaq al-Utaybi, and Basim and Naif bin Awain. Okay, now let's have a look at this example that we have. It's basically a system with reheat and regeneration. We have a high pressure side of the cycle at 15 megapascal and 600 degrees centigrade. This is essentially this is the exit from the boiler, which is this, and then which is leaving the high pressure turbine is going to be reheated back again. So it is sent to the boiler to be reheated to the same maximum temperature, which is 600 degrees centigrade. But this is occurring at a low pressure or at a lower pressure of 4 megapascal, which is points 10 and 11. At this pressure, it is going to be reheated, going back again to the turbine, where it will expand until another pressure, which is 0.5 megapascal, at which a part Z is going to be extracted that will go to the open feed water heater. And after that, the rest, which is 1 minus Y that has been extracted here, minus Z extracted here, and the 1 minus Y minus Z is going to leave the turbine, go to the condenser. It will be condensed to saturated liquid at state number 1, where it will be pumped to state number 2. At state number 2, it will enter into a feed water heater to mix with the steam which is coming from the low pressure turbine, and then that steam will condense here, and the resultant, which will be this quantity, 1 minus Y minus Z, plus Z, which will be 1 minus Y, going through the pump here, where it will be pumped from 3 to 4 in a closed feed water heater, where it will be preheated again up to state number 5. Meanwhile, the quantity of steam that has been extracted at the high pressure turbine, part of it, which is Y, is going to condense here in the closed feed water heater from that state number 10 to state number 6, which will be pumped in pump number 3 to state number 7, where this quantity Y plus the quantity 1 minus Y at 5, they are going to mix together to form the state at 8, which is the total quantity of water that will get to the boiler again. So 1 to 2, again, now I'll be looking at the TS diagram. 1 to 2 in the first pump, and then from 2 to 3 heating, which will occur in the open feed water heater. And then the pump is going to increase the pressure from 3 to 4. And then 4 is going to get into the closed feed water heater. Actually, it will be 4 to 5. 5, it will be the entrance to the mixing chamber, where it will mix with the state at 7, leaving the third pump to get us at the exit or at the end, state 8, in which it will go through the boiler, where it will be heated up to state number 9. It will expand up to state number 10, which is at 4 megapascal pressure. Part of it will be extracted here to 6, where it will be pumped to 7. The rest is going to be reheated in the boiler to state number 11, and it will be expanding after being reheated to state number 12, where a part will be taken, which is Z, to be going to the open feed water heater, and the rest, 1 minus Y minus Z, will go into the condenser to be condensed here. So this is some sort of a typical power plant process that has a reheat and regeneration. What we need to do now is to analyze this problem, calculate how much is the energy in the boiler, either for the whole stream, which is going from 8 to 9, or the reheated stream going from 10 to 11. We need to calculate how much is the heat rejected, which is normally take place in the condenser, which is right here. And we need accordingly calculating Qn minus Q out should get us the amount of power to be given by the turbine. And we also need to calculate or to come up with a value, which is what will be the value of efficiency of this system. Now, before into this kind or into analysis of the problem, there are some issues that that we need to agree upon together. The issues here would be, what are the fixed values that would stick to, or some sort of hints that we might go ahead with assumptions. First is Muhammad Mutlaq معنا. Did he join us?
Yes, doctor.
Okay, fine. So in addition, Naif bin Awain.
يا دكتور موجود.
Okay, fine. So now we have everyone. So you can press again on that yes sign so that it will be clear. Now there are a few things that we need to keep, and I just put it on a separate piece or a separate file that I'm going to upload to the Blackboard as well. The high pressure side, we have 4 states there. State number 4, state number 5, state number 7, state number 8, state number 9. These are all the high pressure side. And on the TS diagram here, they are 4, 5, 7, 8, 9. These are all at the high pressure side. On the schematic, this is state number 4. See, it's going in a closed pipe here. So state number 5 is the same. The mixing chamber dictates that all of the elements around it to have the same pressure. So 5, 7, 8. And then Going through the boiler, it's the same pressure, which is 9. So the 5 states, 4, 5, 7, 8, 9 are at the high pressure side. Then the lower pressure, which is at 4 megapascal, this is basically the extraction that happens here from the high pressure turbine. These are states number 10, states number 11, and state number 6, which is this. So these are all at 4 megapascal. Then the other extraction, which is coming from the low pressure turbine, we have state number 12, which is this. State number 2 and 3, and open feed water here again, is going to have all the inputs and outputs at the same pressure. So the 0.5 megapascal is for states number 4, number 12, number 2, and number 3. And then finally, the final expansion occurs to state number 13 and state number 1, which are at the condenser pressure. So we have 4 pressure levels here. Again, quickly, going from bottom to top, the very low pressure, we have states 1 and 13. Here they are on the TS diagram. And then we have the first intermediate pressure, 0.5. We have the pressure points 2, 3, and 12. And then the little bit higher pressure, in which we have the extraction from the high pressure turbine, we have states number 6, 10, and 11. Finally, the highest pressure we have 4, 5, 7, 8, and 9. Now, assumptions that we are going to do so far for this example, we are going to assume that compression and expansion are isentropic. So S9 is equal to S10 from here. S11 and 12 and 13 is the same entropy. 1 and 2 share the same entropy. 3 and 4 have the same entropy. 6 and 7 has the same entropy. So we are talking about an ideal sort of a cycle. Then next one is that the enthalpies or the conditions, let's talk about the conditions before inlet to any pump is saturated liquid. So number 1 is saturated liquid. So we know the pressure and quality X is 0. Number 3 is saturated liquid. We know the pressure and the quality X is 0. Number 6 is saturated liquid. We know the pressure and the quality X is 0. You can see them in the saturation pressure line. State number 1 is here. State number 3 is here. And state number 6 is here. All of these are saturated liquid. Pressures are there and the quality is 0. This will help us identify the enthalpy quickly from the property calculator and easily.
So Doctor, why the quality is 0?
Actually, normally what happens in the condensation process, this is basically steam which is condensed here, steam condensed here, and steam condensed here. We assume the condensation is going to result in all the vapor has been converted into liquid. So quality is 0. Is that what is happening in reality? Not necessarily, because sometimes you can condense the water to temperature below 1, so it becomes compressed liquid. But that is not, this is very actually is something like 4% of the whole heat exchanger area will be utilized in subcooling or compressing. So that's not a big deal. So it becomes like an accepted thermodynamic assumption that whatever is being condensed is condensed to saturated condition, and then the inlet to every pump is going to be saturated liquid. So it's an assumption, but the assumption makes sense. Okay?
Okay, thank you.
You're welcome. One more thing here which we are going to assume is that we do not have enough information for state number 5, except that we know what is the pressure here. Pressure of 5 is the same as the high pressure of the boiler, but we don't have another state that will tell me what's happening in 5. So what we have to make, either if you are in the plant, we have a pressure gauge and a thermocouple or a thermometer that will tell us what is the temperature and pressure there. But on the paper, we don't have that, so we're going to make an assumption. The assumption is, we are going to assume, look at the TS diagram here, we are going to assume that points 5 and 6 are at the same temperature. Point 5 is compressed liquid. Then we have a rule here. A compressed liquid, normally you would need two independent properties. One of them is the temperature, the other one the pressure, for example, or temperature and entropy or whatever. But here we do not have this kind of detail. So a rule for compressed liquid is that you can take any property of the compressed liquid as the property in the thermodynamic table of saturated liquid at a given temperature. Again, we are going to assume that the enthalpy of state number 5 is equal to the enthalpy at this temperature T5 and at x equal to 0. The same thing applies for any compressed liquid property. The compressed liquid property, enthalpy, entropy, specific volume, internal energy, whatever. You are going to treat it as saturated liquid at the given temperature, not the given pressure, at the given temperature. And this has proved to be a valid assumption, and you can get to the properties, property calculator, and you can try it in your own. So any compressed liquid property, if we know the temperature, we can get the temperature, the property at this temperature for saturated liquid, which is x equal to 0. So in that sense, we are going to consider that the enthalpy of 0.6 and enthalpy of 0.5 are the same. And I'm repeating that this is an assumption. So that the conditions at temperature here 6 and 5 are the same, as if in this heat exchanger, the water has been increased in temperature from 4 to 5, and steam has condensed so that it has gone from this point, 0.10 to 0.6, which is at the same temperature of 5. So I have two streams of that heat exchanger, and they are assumed to be at the same temperature. We know it well. 0.5 is the one that we don't know, and we are doing this assumption. Yes.
دكتور مو المفروض 0.5 يكون البريشر حقها 15 ميجا باسكال؟
Yes, that's right.
How we are assuming that
5 has a pressure of 15 megapascal. 0.6 has a pressure of 4 megapascal, but the temperature is the same.
Okay, but we are assuming that they have the same pressure?
No, we are assuming only same temperature, not same pressure.
Same temperature.
Not the same, but temperature is the same. This is why the rule I talked about, that for compressed liquid, 0.5 is basically compressed liquid. Here is it.
Yes, yes.
And for compressed liquid property, you can get it as saturated liquid property at the same temperature, not pressure, at the same temperature.
Okay.
Doctor, I'm still not understanding why 0.5 and 6 have the same enthalpy.
Because they are at the same temperature.
Okay.
0.6 is saturated liquid at a pressure of 4 megapascal. 0.5 is compressed liquid at a different pressure, 15 megapascal. But we assumed it to be at the same temperature at 6. And for compressed liquid, what matters is the temperature, not the pressure. I'm talking about the properties. In other words, for compressed liquid, say we are talking about water at, for a compressed liquid at a certain temperature. Say the temperature is 90. You can get enthalpy of water at 90 degrees as the same as enthalpy of water at saturated condition of 90. The one has a pressure of 100 kilopascal, the second had a pressure of maybe 80 kilopascal. But because temperatures are the same, then we are basing our equality based on the temperature.
Doctor, for 5, if we want to use the calculator, what is the values need to enter to?
You cannot use the calculator here because you need two independent properties. And you don't have two independent properties, you only have the pressure.
We assume the temperature.
Point number 5, we have only the pressure. We don't know the temperature. That's why we assume that the temperature to be temperature of 6. Use the pressure of 15 kilopascal and temperature of state number 6. It will give you the value which is exactly the same or almost exactly the same as H of 6. Try it with your property calculator.
Doctor, just a quick point. These assumptions will be given to us in the test?
Yes.
Okay.
Yes, I can put it there, no problem.
And along with that, we will be having the figure on the left alongside with the TS diagram with it? Or we need to come up with the TS diagram?
Normally, I mean, when we teach this for the first time, we just give the figure and we ask the students to come up with a TS diagram. I think because basically you're not taking a course for like what happens with the undergraduate students. Whenever you are going to work in a power plant, basically you can have all the charts in front of you.
Mm-hmm.
So I think having you providing with both of them is not going to be a big deal. That's fine.
Thank you.
But at least you should understand how to match between the points in the left and points to the right. This is what really matters in. Like the states 1, 2, 3, 4 up to state number 13 in the schematic, and the same thing on the TS diagram, because that will enable you to calculate the properties and do the analysis. Now, having put all of this, when we look at those states that we have and looking at what we know about each state, let's take them point by point. State number 1, what do we know?
Pressure.
I'm looking at
Quality.
We know pressure and only pressure.
No, not only pressure. We know something else.
And the quality X is.
And the quality. The pressure is 10 kilopascal and the quality is 0.
How did you know that the quality is 0?
Because I said before, when we are talking about the assumptions, this is inlet to the pump. And any inlet to the pump, we're going to assume quality is 0.
Okay.
So 0.1, 0.3, 0.6, the quality is 0 for the 3. So the enthalpy of 0.1 can be obtained easily from the property calculator. Now, second, state number 2.
We'll call it superheated.
No, saturated liquid here. This is the saturated liquid line. So this is saturated liquid. This is what X equal to 0 means.
Okay.
State number 2, we know only the pressure. So we cannot right now obtain the properties, the enthalpy of point number 2. We cannot do that at the moment.
But we know the entropy, Doctor.
That's a very good point. We can say that the entropy is at 2 is equal to the entropy at 1, and then you can get H2. Yes, this is one way to do it, which is one good way to do. Another way that you can calculate the work on the pump. Work on the pump is the specific volume V into the change of pressure. You can add the work of the pump to enthalpy at 1, you can get enthalpy at 2. So obtaining the enthalpy at point 2 can be done by either assuming that the entropy on 1 and 2 is the same, but 2 is at a pressure of 0.5 megapascal. So you have two properties now for 2. One of them is the pressure, 0.5 megapascal. The second is entropy at 2 is equal to entropy at 1. Or you say that I'm going to calculate the work of pump number 1, which is, you know, the work for the pump number 1 can be written as H2 minus H1, and it's also V into P2 minus P1. The pressures are known. Specific volume you can get from state number 1, and then you can after that calculate this this work added to H1, and then you can get H2. So there are two ways to do it.
This is
Now,
the general way, doctor, right? For example, this way we'll be using it, or this equation will be using it for ideal or non-ideal cycles.
exactly. I mean, working with the entropy is going to allow you to do it better. Because if you have a pump efficiency, only the issue of the enthalpy is going to help, the entropy is going to help you with.
Okay.
Like what we did in our previous, on Saturday, and when we talked about it on Tuesday also. State number 3.
طب دكتور بس sorry, state number 2
But
is saturated liquid as well.
it's compressed.
Compressed liquid.
Compressed liquid, yes. Then state number 3, what do we know?
So the pressure.
Pressure
and the quality.
And the quality equal to 0, yes. So we can get H3. 4.
When a specific volume, the pressure.
And
entropy.
And entropy. Entropy, which is this. It's the same as entropy of 3 because we're talking about an ideal case. So here we know pressure, we know specific volume, and we know entropy as well. So you can use two of them and get what would be the enthalpy here.
Doctor, will it be possible that you write down while you talk so that we can
I'll be sharing a file with you that has this information because I mean it will be very crowded this slide as we look at it. But I have the next slide actually having these values, but I just want us to look at it on the figure first. When I move here, you'll find that I'm writing what we know there. But I just want us to look at it here while we are looking at the figures. Is that okay?
Yeah, sure. Thank you very much.
Okay.
Doctor, can I get H4 by -3?
H4 minus H3 is equal to the work in this pump, which is the specific volume into P4 minus P3. Like what we did here for 1, we can do for pump number 2 as well. But instead of 1 and 2, it will be 3 and 4.
But doctor, when getting from the property calculator, the state for number 3 will be different than the state of number 1, right? I need to change the
Yes,
state.
of course, because this is at a pressure of 10 kilopascal. This is 500 kilopascal.
And temperature.
No,
and
I mean
the temperature will be different, definitely.
The medium.
So the states are not going to be the same.
So I should change there is some property where you put dry air or whatever. I should put it.
No, definitely you are going to work with water for all of them.
Water for all of them.
All of them water. Because it's a steam cycle.
All phases, Doctor.
Excuse me?
All phases from 1 up to 13 by water?
Yeah, from 1 to 13, it's all H2O. Whether the water is in liquid or vapor phase, but it's all H2O. There's no air. Air will be used only when you get to the gas turbines. But as long as we are talking about steam power plant, it's only water. Then, state number 5, we'll leave it at the moment. We'll not talk about it. But let's go for state number 6. In state number 6, what do we know? We know the pressure, 4 megapascal, and we know quality, X is equal to 0. State number 7, what we did between 1 and 2, 3 and 4, we're going to do between 6 and 7. Here, S7 is equal to S6, and the pressure of 7 is 15 megapascal. We can get H7 then. We'll leave 8 at the moment, and then we'll go to 9. What do we know about 9?
Pressure?
Pressure and temperature.
Yes, we know pressure and temperature. Pressure is 15 megapascal, and temperature 600. So you can definitely get what will be the enthalpy, and you will need the entropy. So at 9, you are going to get H and S from the property calculator. Why S? because we will need that in state number 10. State number 10 is having a pressure of 4 megapascal and it has an entropy equal to 9. So this way we can get what will be H for state number 10. Then it will go at 10. What will happen? Some extraction will happen. A Y value is going to be taken from the vapor there, and this is what has been expanded, what has been compressed in the third turbine, and the rest is going to be reheated to state number 11. State number 11, what do we know? We know the pressure, 4 megapascal, and what else?
Temperature.
State number
What else do we know?
Temperature.
Temperature, which is
600.
600. So we can get the enthalpy at state number 11. Not only enthalpy, I need enthalpy and
entropy.
Entropy, because we are going through an expansion.
طب Doctor, I'm sorry to interrupt, but
No, go ahead, please.
We're solving this example to find يعني what's the end result.
This is what I mentioned at the beginning. We need to calculate how much is the heat added, how much is the heat rejected, how much is the work, and the cycle efficiency. So what we are doing here is called performance analysis, rating. We are rating the power plant. It means that we need to see how much is the work done, net amount of work obtained by the power plant, and what is the power plant efficiency. This is the target. Then, going from state number 11, we're going to expand up to state number 12. State number 12 is characterized by a pressure of 0.5 megapascal and
S12 is equal to S11.
Exactly, and constant entropy. S12 is equal to X11. So we can get the property here, the H. Go to 13. The pressure is 10 kilopascal and S is equal to S12 and S11. So you can get the enthalpy at state number 13. So now we have got the enthalpy in all the points except 5 and 8.
Yes.
We are going to make the assumption. The assumption that we did is that H at 5, sorry, H at 5 is equal to H at 6. We're going to take this assumption. So now this 5 we have taken care of. The only thing left is going to be the enthalpy at state number 8. And the enthalpy at state number 8 is going to be obtained from the energy balance of that mixing chamber. So we have this mixing chamber here. And we're going to make an energy balance for this. There is a quantity passing here. And this quantity basically is 1 minus y coming in here. And it has an enthalpy of H5 that we know. So 1 minus y all multiplied by H5 plus y multiplied by H7 is equal to H8. H8 is 1 minus y plus y, so it's 1 kilogram per second. We are working the whole thing per 1 kilogram per second. So 1 minus y into H5 plus y into H7 will get us H8. Now we know the properties for all of the points that we have. Let's look at this in the table. I'm talking about for each point, what are the properties that we know and our calculations then. So at state number 1, we know pressure and quality, we get the enthalpy. State number 2, we know the pressure, but we have already talked about how to obtain the enthalpy here, which is either by having S is equal to S1 or by calculating the work. State number 3, again, we know pressure and quality, we obtain the enthalpy. State number 4 is again after having a pump. So what we did with state number 2 will be repeated here, but at a different pressure and temperature. State number 5, I'm writing the assumption that H5 is equal to H6. State number 6, it's again saturated liquid. So we know the pressure and quality. I should have written the quality here for state number 6. State number 7 is again what we did with 2 and 4 would be repeated here. State number 8, this is coming from the energy balance of the feed water heater, of the mixing chamber. State number 9, we know pressure and temperature. State number 10, we know pressure and entropy. State number 11, it's a typo here, it should be P11, which happen to equal P10 anyway. And we have pressure and temperature. State number 12, we have pressure and entropy. State number 13, we have pressure and entropy. So now all of them are going to be calculated directly from the property calculator, except for 2. I mean, two types of states. One of them is the exit of the pumps that makes states 2, 4, and 7. We are going to make use of the constant entropy between 1 and 2, and between 3 and 4, and between 6 and 7. And the assumption we made between 6 and 5, H6 is equal to H5. And finally, the energy balance of the mixing chamber that will enable us to get the value of H8. I think I have these equations written here.
Doctor?
Yes.
Can you back to the slide one before?
This one?
Yeah, this slide. Now,
okay.
When the pressurized vapor comes to the turbine at step number 9, and that means it comes to the high pressure turbine, and after that, when it loses its pressure, it goes to the low pressure turbine.
Exactly, it's going to expand, and at a certain pressure, which is 4 megapascal, we are going to make an extraction. This extraction, we're going to take a certain quantity of the vapor Y, and we're going to send the rest to the boiler for reheating. After reheating, that steam is going to enter the low pressure turbine where it will expand again.
Okay, what's the difference between high pressure and low pressure turbine in the design, or in the blades maybe different? Or...
Yeah, and in the high pressure turbine, the blades are short and thin. In the high pressure turbine, they are long and a little bit wider. So I'll be sharing with you, I think last night I just found one link. I think it was in LinkedIn or so. Somebody sent like a video that simulates the process that probably I'll share with you. I hope this one has this kind, it would show you that the difference in the size between the turbines as you are moving from high pressure to low pressure. So the way the blades are being designed is a little bit different.
Doctor, about 13, it's written 1 minus Y minus Z.
Yes, this is the amount of steam which is reaching there. We are talking about per 1 kilogram per second of steam. We have extracted a certain quantity here at Y, and then
be given
a second quantity here at Z. The remainder is going to be 1 minus Y minus Z. In reality, it should be 1 minus Y minus Z, all of it multiplied by m dot of steam. Here we say that we're assuming we are working with 1 kilogram. Here is it. Suppose it's 50 kilograms, and you have taken like 4 here and then 5 here, then the remainder will be 41, which is 1 minus Y minus Z multiplied by the total quantity. So Y is a fraction, it's a percentage. Z is a fraction, which is a percentage of that mass which is passing in. Did I answer your question?
Yes, please, thank you.
Okay. Now, we have seen now how we obtain the values of enthalpies. So far, 8 has not been given in details. But remember, the missing values now are not only enthalpy at number 8 that we are going to get from the energy balance, but we also need to know what is the quantity Y and what is the quantity Z. To determine these, we are going to make energy balance for the 3 components. So energy balance for this mixing chamber will enable us to know the value of Y because it has only one unknown. No. Actually, when we are going to write this energy balance for this quantity, for this heat exchanger, mixing chamber, for the closed feed water heater, and for the closed feed water heater, when you look at it, what do we know and what we don't know, you'll find that we know H4, we know H6, which is equal to H5, and we know H10. So we have all the enthalpies around it. What is not known here is the fraction Y. So the balance of energy in the closed feed water heater will enable us to know the value of Y. Having known the value of Y, the mixing chamber will enable us to get the value of H8. Now we know H8, we know Y. When we do the analysis for the open feed water heater, we'll get the value of Z. So, and each of them can be obtained in one step. You can see that here. Here I'm calculating the pump work for each one of them that helped me calculate calculate the further enthalpies H2, H4, and H7 as one way to do it. The closed feed water heater, which is the one in the middle, we have Y, quantity of steam entering at enthalpy H10, which is this. There is a Y quantity here, the flow rate is Y, at enthalpy of 10. This is one inlet. The second inlet here is 1 minus Y at enthalpy of 4 that we don't know, that we already know, sorry. This is leaving at H5, we know it, and the quantity is 1 minus Y. H6, we know it, and the quantity is Y. So the energy balance for the closed feed water heater here, Y into H10, 1 minus Y, H4, 1 minus Y into H5, we know them, we know H5, and Y into H6, and we know H6. So we know H6, which is equal to H5. We know H4, and we know H10. The only unknown here is Y, and the Y here is 0.17. So 17% of the steam has been extracted here at the high pressure turbine. Then the open feed water heater, which is the one to the right next to the condenser, we had a certain quantity extracted from the low pressure turbine at point 11, Z into H11. The quantity coming from the condenser, 1 minus Y minus Z at state number 2 is H2. And whatever is leaving is going to be 1 minus Y into H3. The only unknown here is Z. So Z is 13% of the steam that has been extracted.
دكتور محمد,
used to calculate the value of H8. Yes. Go ahead.
في شيء ما عرفته لسه. What's الواي والزي؟
الواي هي كمية الستيم اللي احنا اخدناه من التوتال ستيم اللي رايح من الهاي بريشر توربين للبويلر فور ري هيتنج. اخدنا منه شوية اللي هي واي. هي اللي دخلت على الكلوزد فيد ووتر هيتر. يبقى ده شوية ستيم اخدناهم هنا. Why did we do that? Because we need to that steam to condense in the closed feed water heater to preheat the water. So we take a fraction of the steam here. The same thing here. We have taken a fraction of a steam here so that we mix it in the open feed water heater so that we can preheat from 2 to 3, from this point to that point, to add this amount of heat. So steam is taken to condense here, a part of it. A part of the steam has been taken to condense here. Did I answer your question?
اي شكرا دكتور ما قصرت.
Okay. Now, having done that, yeah, go ahead.
So at point 10, we have a pressure of 4 megapixel.
Yes,
now,
exactly.
And why we got the 0.17 And the remaining went to the low pressure turbine, right?
That's right, yeah, exactly. And in the low pressure turbine, we lost another 12% or so, 13%, which has gone to the first feed water heater. So the remainder, this is about 31% of the steam. The remainder, which is 69% of the steam, has gone to the condenser.
Okay, thank you.
Okay. Now, one would think, I mean, now instead of starting with a total quantity, say 1 kilogram per second of steam, we have taken 17% in the closed feed water heater, we have taken 13% in the open feed water heater. Wouldn't that affect the power that we are getting? Because what is expanded in the turbine to produce work now has become less. So aren't we going to get less efficiency rather than higher efficiency? And that's what I said, when you are getting something, there's nothing for free. In order to increase the temperature of water before it enters to the boiler, we have sacrificed part of the power which is needed. But this penalty that we did has been compensated by the reduction of Q in needed, the quantity of fuel which is needed to boil the water. And at the end, are we getting a benefit or not? This will be shown in the efficiency. So when we do the efficiency, calculating the energy added, let's look at these quantities, how they are being obtained. When we look at energy added to the system, going back again to the figure here, energy is added, number one, between 0.8 and 0.9. So this energy has been added to heat this water to the saturation temperature, evaporate it, and superheat it to 9. So this is heat added. The quantity is 1 kilogram per second. The whole quantity of steam has been added up to 0.9. And then at 0.9, we make an extraction, taking part of it, which is here, and the rest, which is 1 minus y, has been heated from 10 to 11. So QA is going to equal to this quantity here, H9 minus H8, plus 1 minus y multiplied by the difference between H11 and H10. So this makes the energy into the system. What about the energy out? The energy rejected. It is rejected in the condenser. So what has been rejected here is 1 minus y minus z multiplied by the difference, H13 and H1. And you will find that we have decreased the energy rejected. And that's why the work has been retained. Let's go back again here to this calculation slide. This is the energy in the high pressure, going from the state number 8 to state number 9, and then reheat, which is only 1 minus y multiplied by the enthalpy difference, get us the Qn, energy n. The energy rejected is 1 minus y minus z. It's not the whole quantity. So now we have less energy rejection, which is this. The difference between this value and this value is the work done, or the power. And then the efficiency is 49%. The good thing is that if we remove all the feed water heaters, the one closed and the two open ones, you'll find that the efficiency is 45. So the system now has 4% increase of efficiency. This is a substantial increase in the efficiency of the system. This is too high. This is a very good achievement, being able to increase the efficiency by 4% by just this kind of modifications. We kept the high pressure side 15 kilopascal, the low pressure side 10 kilopascal, but just adding the issue of regeneration has resulted in this increase in the efficiency of the cycle. So 49% rather than 45 if we don't have regeneration. So that was basically the example that I wanted to share with you.
Doctor,
yes, go ahead.
can you return back to the this slide?
Yes.
The efficiency. How can we get the efficiency?
The efficiency.
Output divided by input or?
Yes, exactly. The efficiency here is basically by definition should be what do we get? And the power plants are made so that we can get power. Power is what we are looking for. What we do, we give fuel and burn it in, so there is a QN here. So the efficiency basically is the power that we get, the work that we get divided by the energy added. If you consider your power plant as a whole control volume that having inside it the pumps, the boiler, the turbine, and all the components in, and you look at it, what will enter into it and what is going to leave out? What will enter is going to be QN. What will be leaving is work and Q out. And then when you apply the first law of thermodynamics, the energy conservation principle, the QN is equal to the Q out. What is the the energy out, which is this plus this. Accordingly, I can replace the work by QN minus Q out divided by QN, which is 1 minus Q out over QN. We have already calculated Q out, we calculated QN, and this is where we got the value of 0.49. I hope it's clearer now.
Yes,
okay.
Quick question, Doctor.
Yes.
Now, the energy rejection, it happens at the condenser.
That's
and
right.
How about the energy added?
It's basically added in the boiler. You did not add energy from outside except in the boiler. What we are doing in the feed water heater is something internal. I'm taking heat from the turbine going to the feed water heater. It's all internal. It's all happening inside this box. But across the system as a whole, there is fuel that is added to the boiler. You did not add fuel to the feed water heater. It's only to the boiler. So this is the only QN coming to the unit. And because we have water from the lake or the Gulf or the sea coming in, it will get in, it will be heated, and then it will leave at a higher temperature. So there is energy rejected to the surrounding. And the unit here is connected to a generator. So there's energy which is crossing the control surface. So this is what we are looking for. What comes into the whole system and what goes out from the whole system. So adding energy in terms of steam, which is leaving one component and going to another component, that's something internal. It did not cross the boundary.
Clear. Yeah, that is clear, but it will be very helpful if you explain it in the previous page, like 8.9, sorry, there were one previous before this one and before, sorry.
We're here.
Yeah, we're here. So
Fine.
It's point 8 and 9. This is at the boiler, and then points 10 and 11 are after the high pressure turbine. So how is the energy added here? I'm not getting it.
The energy added here, I did not add more fuel. But what happens here? I'm talking about a boiler in which there is fuel burned and there is very high temperature inside here. Is this high temperature has converted part of that, or have converted, sorry, all of this fluid here from compressed liquid to superheated vapor. And then it has expanded here, and by expansion, its temperature, its pressure has reduced. You are going to take this steam in a pipe and make this pipe go inside the boiler again. Then it will return back. It will return back at the same pressure, but after being reheated to this temperature here. When I've done that, I sent it to the boiler internally. Again, I did not, if we consider that we have sort of a, sorry, if you put like, a fence in the old system that we have here, what's going to cross this? I'm going to bring fuel in. I'm bringing it to the boiler, not to a section of a boiler, to the whole boiler. And here there is work, and here there is energy out, because water from the lake is going to come here. It's going to absorb energy from the moisture, from the vapor, and convert it into liquid. So it will come with a low temperature, it will leave with a high temperature, and this is how the energy is being rejected. So what crosses this is only heat input to the boiler, energy output for the condensation, and the useful work that we are getting from this unit. This is an internal part still.
So our starting point in the power plant is in the boiler?
Normally, it depends. Where do you start? Sometimes, like this problem, we're starting from here, from point number 1. We called this number 1, but you can start from any point because it's a cycle. You're going to start from a point, and then you're going to return to the same point again. So define your starting point. If you want to put the input to the boiler at point number 1 and start from there, that's fine. You see, when you have a circle, it doesn't matter where you start from.
But I mean, at the beginning, like at the commissioning of the power plant, I usually start to put the fuel into the boiler.
Yes, to start up the boiler, this is what you do. You put fuel in, but before you turn the fuel in, you have to run the water into the system. So basically you make because the water is the one which is going to absorb the energy. Otherwise, overheating of the tubes of the furnace will occur and it will damage. So first, when you're starting a power plant, and the start up of a boiler or a furnace, generally it takes a few days. What you do, you run the water, cold water, you run it everywhere. Make sure that water is not leaking anywhere. Then second step, you're going to turn on the fire, and then definitely when you are running, you cannot run cold water in the turbine, otherwise you'll damage it. So the point is, you have to make sure that the boiler tubes are filled with water before you turn the fire on. Water is the one which is going to absorb this energy. And by the way, it's a whole kind of profession. You can find some engineer, and this engineer, his basic work is furnaces starting up or shutting down. I mean, it's some sort of a complicated steps that needs to be done to make your system is safe while doing that. So it's not like a knob that you are going to press on or off. It's a little bit more complicated sort of procedure that you have to do to get the system running on. But in our analysis, we are talking about a system which is continuously running on. We did not talk about how to start it up or how to shut it down. Addressing your question, I didn't go too far.
Yeah, that's perfect. Thank you very much.
Okay, thank you.
Dr. Mohammed, I have worked in a gas oil separation plant, and there is something there called reboilers. Okay. It has the same concept of the boiler, because it's steam. What we have
actually, reboilers would be doing that. You can use steam for them to heat up a chemical. Maybe this chemical could be crude oil to decrease its viscosity so that you can pump it easily.
Exactly what this is for.
It is nothing. I mean, a boiler is nothing but a heat exchanger. So basically, we need to transfer heat from one fluid to the other. In our case here, the fluid is the flue gases. You have fuel that you are burning, so you need air. Fuel will burn, and then the air is going to be heated, and the flue gases, the combustion products, are the ones that are at a very high temperatures. So this is the first fluid. Second fluid is the water inside.
Okay. And there is like big bundle.
Convert it into steam. Another system, we take that steam and use it to heat maybe seawater to bring it to very high temperature in a desalination plant, or a chemical. so that you can work on its viscosity to be less, and then you can pump it easily and so on. So they are basically heat exchangers, not necessarily boilers.
Okay, heat exchangers which transfers heat from one medium to another.
Exactly. I mean, a boiler is one type of heat exchanger. Feed water heater is a type of heat exchanger. Condenser is a type of heat exchanger.
Okay, okay.
And let me tell you also that although we don't have it here, but a cooling tower is another type of heat exchanger.
Okay.
The other one, the cooling tower, we call it heat and mass exchanger. But anyway, the principles are not too far.
Thank you.
Yeah, you're welcome, sir. Having reached to that state, covering this example, I have to tell you that I've already placed homework number 1 on the system, on the blackboard. It is made up of 3 problems. The first one is a very simple problem just to get your hands running. The second one probably would be some sort of a reheat problem. The third problem is this example. Exactly the same example with numbers and pressure levels and everything as being the same. But guess what is the difference? Who can tell me what would be the difference?
المطلوب يكون مختلف.
Yeah, definitely. Otherwise, you'll be copying it.
Aim extraction from the main line.
No. I mean, extractions are going to be exactly the same as we are putting here. The only difference is that I'm telling you, assume that the turbine efficiency is 80% and pump efficiency is 90%. So the issues of compression and taking care of the entropy and taking care of the efficiencies to determine the exact or the actual point of exit from each pump and turbine would be there. So that's the only difference which is there. So
can you repeat it, Doctor? What's the difference?
The difference is that I'm providing you with efficiency of these processes, which means that when you are talking, for example, let's look at point number 3. It will be basically, this is 4S, and actually the actual 4 will be somewhere here. 4. So that you are going to use the expression of eta pump to get the value of 4. So that eta pump is H4 minus H3 divided by H4S minus H3. You have this, so that you can get state number 4. Same thing for the turbine. This is 9 and this is going to be 10S. In reality, it should be something like this, 10 actual. And then the efficiency of the turbine is going to be H9 minus H10 divided by H9 minus H10S. You have H9, you have H10S, you have the efficiency so that you can get the point 10. And then the expansion is going to be, let me show you here for 11, because this is interesting here. At 11, actually, you are going to go from here. This is a constant pressure line here, sorry. This is a constant pressure line that should extend. So from 11, you are going to get to the point here. This is going to be 12 actual. And from 12, this is going to be vertical, and this is going to be 13 actual. So it's this kind of little change that it's not a much of work, but it just shows that you understand fully what's happening in a system like this.
Doctor, just a quick question. The turbine efficiency applies for both high pressure and low pressure.
Yes,
so
yes, exactly. It will apply to all.
Okay.
Okay.
دكتور محمد
اتفضل.
اسمح لنا الله يسلمك بريك قصير بس كذا 5 دقائق.
عفوا. Yes, actually after finishing this example, I just wanted to pass the information. One of them is this about the homework. And next week, we do not have class. As you see, the way the modules goes is that we have 3 modules and within 1 week, one Saturday off, and then something like that. So we'll be starting after a couple of weeks from now, and I think Dr. Mukhemer will be there to start on the gas turbines. Now we are going to break for about 5 minutes and then continue the last something like 30 minutes or so talking about something a little bit different from what we had so far. Now it's 3:22. Probably let's extend it to 8 minutes and get back at 3:30. Then we'll have like half an hour presentation talking about engineering economics or so. So see you after 8 minutes from now.
Doctor, just I want to make sure, يعني after this session, you will not be with us anymore?
No, I'm coming back again, but a little bit later. You are going to have a coverage with Dr. Mukhemer for the gas turbines and part of the solar energy. And then 1 week, Dr. Naqvi will come from the physics department talking about nuclear power plant. And then I'll be back again talking about other features of the solar energy. So you'll be seeing me again after that. Actually, I'll be there every week with you. But next week, Dr. Mukhemer will be the one taking the lead and explaining the gas turbines.
I was asking, كنت أسأل عن هذا عشان الاختبار يا دكتور. يعني قبل الاختبار we should only understanding the homework will be enough.
Yes, actually, I'm going to talk about it also when we come back after 7 minutes or so. So I'll start about the exam and then we'll move from there. Okay. Okay, Assalamu alaikum.
عليكم السلام.
Are you able to hear that sound يا شباب ولا لا اللي جاي؟
ما نسمع الصوت.
It's not clear, doctor.
الصوت مش واضح. So what I'm going to do is that I will try to put the link على البلاك بورد بحيث ان انت you can see it يعني.
طيب.
It would be better than just putting it like this يعني. Okay, so I'll stop sharing this one and then I'll make the link available in Blackboard.
Available.
Fine. There's again probably I'll just ask you to do the opposite. Last time after a game from the break, I asked you to click on the yes so that I can see the green checks here. Can you press on the yes again so that we can we just need to clear this. So if you have it checked, please press again so that it will be unchecked. Okay.
السلام عليكم دكتور.
عليكم السلام ورحمة الله.
يرز معتز القحطاني.
أهلين يا معتز.
دكتور عندنا اختبار مادة ثقيلة شوي في 3 أكتوبر وإحنا نبغى نعطي المادة هذه وقتها. في مجال يا دكتور نأجلها إلى 10 أكتوبر.
For me بالنسبة لي أنا it's okay ما عنديش أنا مشكلة. I just need to check مع الكوردينيتور. I mean is there a must إن المسألة تبقى يعني مع البروجرام كوردينيتور. بالنسبة لي it's okay. I don't have a problem. So I'll just confirm it مع دكتور مهيني and I'll send you I'll put it in the notifications in announcement في البلاك بورد. بس مبدئيا it's fine with me.
يعطيك العافية يا دكتور.
الله يجزاك خير يا دكتور لانه بالفعل يعني بنواجه مشكله صراحه في الوقت هذا.
طيب خير ان شاء الله.
يعطيك العافيه دكتور.
الله يحفظك. وزي ما اتفقنا بالنسبه للاوفيس اورز يا شباب احنا اجين يوم الثلاث ان شاء الله برضه في نفس الميعاد الساعه 6 او البي ذير ثرو زوم او send you the link and then ميعاد الراحه بتاعكم في العمل امتى؟ من الساعه كام؟ من 12 لواحده مثلا للكل ولا ايش؟
بالنسبه لي يا دكتور من الساعه 6 الصباح الى 6 المغرب.
مفيش بريك في النص؟
لا بعضها يا دكتور ما في بريك.
واو.
ولا النت صعب يا دكتور.
خلاص هو عموما يعني احنا اتفقنا يوم الثلاث هيكون الساعه 6 بعد الظهر، انما مثلا ايام الاحد والاثنين والاربع انا هكون موجود الساعه مثلا 1 بعد الظهر. You can find me على Teams. If it does not suit you and you have questions, just send me an email and then we can set a time. If you needed further like discussions or something which needs clarification, just either I'll just put the dates again on the blackboard so that you would know it on the Teams as well as on Zoom, inshallah. So there is one thing. Second احنا اتفقنا بالنسبة للإجزاء.
في ناس يبون يدخلون السيشن.
في أنا شايف نايف بس is looking for joining.
Yes.
Okay, I have something to share with you now, which is regarding the engineering economics. I'm not an economist myself, but the point is, I need to go quickly through different ways that people use for evaluating viability of a project, whether to be considered or not. And definitely you are going to get more than that because you have a course which is dedicated for the economic part. So just going quickly through it so that you can get some sort of a quick overview. It will be a part which is covered in the book in chapter 3. And there is a couple of examples that were given shortly in the book. They needed elaboration. So I made them in Excel file, and the Excel files are in the Blackboard already. So that if you want to see the details of how these numbers or where they come from, then you can see them there. It's basically the chapter, you can read it all in your own. I'm just here covering some sort of headings of information in the chapter. So, I mean, you don't need me to go through it in details. This is one thing. The second thing, because at 4 o'clock, the time the class should be over. So just right after the class, I made a Google form again. I shared the link with you in Blackboard, which is basically in a way that I need your feedback. It has basically 3 questions. One of them is, what was the most interesting that you have seen in the previous 3 modules, today, last week, and the week before? And what was the least interesting? And then what you think you can propose to make the classes more interesting and more beneficial. So that's sort of a feedback that I would like to make and probably share with my colleagues so that we can tune the way that the course is going so that you can get maximum benefit and it would not be boring with this kind of technical information one week after the other. So please get into this after you finish the class and try to fill in. Feel free to write whatever you like. What is it that you liked? What is it that you did not like? And what is your proposal for getting things? And then we'll see if we can meet some of your expectations. Then that would be great.
Doctor, me.
Yes.
We'll begin with this slide. Now, this slide, is it related to the exam, engineering?
No. What I'm covering now is not related to the exam. I'm not calling you to leave now, so just bear with me.
Yeah, I know, but just...
no, it will not be a part of the exam.
Yeah,
okay. As I was telling you, I'm just giving some sort of headers here, and then you are going to get a lot more in the economics in another course. So this is just to get into the basic idea, that's all. So the introduction or the objectives basically is to have just sort of a quick overview of economic tools related to the energy systems. Most of the energy systems or projects are scrutinized for cost effective. People are looking at more and more details and specific because at the end, the project has to be cost effective. One way you should convince the owner or the operator of the good use of resources. The external funding agency, you have to convince them that the project is worth financing so that you can guarantee financing for the project. Also, some decisions that can be done over with a society collective input. Or the majority of people has to be convinced of this kind of project, and then they are going to support it. The project doesn't have to be over budgeted, and it doesn't have to be underestimated, under investment or underestimated as well, because both of them are not going to affect the performance of the project and whether you may neglect or consider the existing stock of energy or the infrastructure, the way that things should be kept. For example, you can have a very sophisticated network of trains, but you don't have enough investment to not only to maintain it, but to keep it running and expand it. So under investment there is going to be a problem. So the issue of over investment makes it very costly. Under investment affects the performance of a project. The cost of energy is one of the most crucial factors that affect us, because that is going to make the energy available. And as we have seen in the introduction, availability of energy more and more is a measure of prosperity of communities as well as countries. The whole idea that the chapter is going around is that the value of money decreases with time. if you have a dollar 10 years ago and you can buy something, right now you cannot buy it with a dollar. You have to spend more than that. So the value of the money is going down, and it is going down by several factors. One of them, or the major factor, is the inflation. Investors expect to have a return on investment. Even when you put your money in a bank, you expect something to be coming back that would not make the value of money go down, at least to keep the same purchasing power of your money. The number will increase in the account, but will it be able to buy the same thing it used to buy 10 years ago or not? This is the issue. And what about even making a profit out of that? So these are some of the issues that the whole chapter is centered about. And the idea of time value of the money was one of the things that were looked at, with great focus. Tracking the inflation is very important. And even given some sort of an index to measure that. And governments usually go to a kind of box with some major elements that people are using for buying, and they make what's called the consumer price index, so that a certain amount of goods that are collectively together, and even there are applications on the mobile. Some of them apply to the current status in Saudi Arabia, and then you can get that. I mean, it's a group of goods that people buy always, and what's the total price for this group of goods that increase or decrease with time. This has been done in the US and UK in a table here, which is this table. In this table, they are considering the consumer price index in the United States, United Kingdom, and they are taking the year 2000 as a reference. So a value of 100 has been specified for this year for both UK and US, and everything has been normalized with respect to that. So whatever you used to buy by $100 in US in year 2000, you could have bought it for only $87 in 1997, and now you need to spend, like in 2014, you need to spend $137 to get the same thing. So that's some sort of a inflation here.
هذا البرودكت معين ولا in general يعني؟
It's in general. It's like a selective basket of goods.
Basket, okay.
But here it is basically geared toward the energy sector. I looked for something similar here in Saudi Arabia as I was browsing, and I found that this one, that the CPI index in case A in the last 20 years, and it shows you here from year 2000 up to July of 2011, and you see here that the little peak which is occurred in July, this is basically due to the new tax of 15% that made this point jump a little bit here, and then after that I think that it will stabilize. So that's some sort of an indication over the years for this consumer price index. How can we make use of it? An example can be given, for example, to distinguish between the prices increased due to inflation and prices increased due to other factors. The current dollars, how they are worth further or compared to the adjusted dollar. Adjusted dollar, it means, or the constant year dollar is the value of the dollar that can buy the same thing at any time over the years. Example is being given here. A model car, you could have bought it for $17,000 in 1998. And in 2005, the same model, say we're talking about, say, Toyota Camry, somebody could buy it for $17,000 in 98, but the same Toyota Camry is bought, I mean model of the year definitely, for $28,000 in year 2005. Given in the face value of dollar for each one of these years. Now, is that a natural increase due to inflation, or the other factors come in? So to do that, what basically want from this example is to evaluate the price or the value of this 17,000 in year 2000 by the level of dollar in year 2002. And do the same thing for this. The 28,000 in 2005, what is worth in 2002? And then if it's only the inflation, they should come to the same value. If there's more than the inflation, then it will be different. To do that, we are going to make use of this index here in the year 1998, which is the 94.7, and the year 2000, which is 113.4. So, and definitely the year 2002 is the one that has this, this value of 104. So we're going to normalize between this value and this value, and normalize again between the 113.4 in 2000 and the 104.5 in 2002. And the values are calculated. It's a simple ratio here. You are multiplied by the CPI in this year to that year, and we are getting the 1998 could have had a value of 18,763 in 2002. The 2005 value in 2002 should have been 24,986. But this one is, they are not the same, which means that the increase of price that happens from here to here is not only because of inflation, but there is an increase of price accordingly with this. Probably you could have seen that maybe you were not aware in 1980, for example, what was the price of a sedan car here and what is the price now, and you find that the difference is big. So now the issue is, are we able to compare or not? Now for this example, we had to normalize it over a certain value of a dollar over a year, and accordingly we could judge whether the increase is only due to inflation or not. We will need to do that for investments in projects in general, and that's why came the idea of present value, future value that can be used to take care of this issue or the inflation issue. So the CPI is going to show options, which is, should we invest now or should we not invest, or should we invest the money on something else? That's an issue that the CPI is going to help us with. For us as consumers, we have the consumer product index, but for the manufacturers, they have another index, which actually is concerned with the kind of input, whether it is investment in the capital cost or the running cost for the plants, so that they can see whether it is, are they able to sustain their business or not. And the issue of having the money value decreases with time has been considered in what's called discounting, which means that it takes care of the reduction of the price or the value of the money as time passes. I got this, this definition of discounting from Investopedia. It's called the process of determining the present value of a payment or a stream of payments, could be annual payment, for example, and showing or reflecting the deterioration or the decrease of the value of money with time. Now there's some terminology which are always used, talking about an energy project, for example, that somebody is going to invest on, and this project is going to last for how many years before it becomes obsolete. This is basically what's called the terms of a project. What is the project lifetime? It's given in years, capital N. Initial cost, basically it's related to the assets. The annuity here comes two things, whether the cash flow in, the cash flow out, which are the expenses, and the net value, the net positive value. If it's positive, then it will be good. If it's negative, then it will be a problem here in the system. So it can be considered as a net amount of flow after considering the positive and negative flows in and out, so that a project should have a positive annuity to repay for the investment cost. Otherwise, it will be losing and failing. The salvage value is the value of the assets toward the end of the project. Suppose that somebody has bought a car and he's using the car for 20 years, what's the value of the car after the 20 years? This is the salvage value when he's going to just get rid of it. Evaluation can be done with or without discounting. And now the time domain is important, because you may have a system which is producing, for example, a certain amount of profit now, but over the years, the value of the profits gets down. And this is what's meant by discounting. Is that something that we can consider in our analysis or not? The book is saying simply that for short-term projects, you may not consider it. But for projects that extend for longer number of years, this is definitely a must. If I have a project of about 2 to 3 years, I don't expect the currency to be affected much in that period. It may, but generally speaking, it would not be significant significant change. But the issue is over a longer period of time, that's something which is expected. And there are different ways that you can look at that, and different methods for analysis, which are being listed here in this chapter, and a summary is given here in this in this presentation. Net present value is a way that you can add up all cash flow in and out of a project and calculate what's the net present value currently. If it's positive, then the project is financially viable. If it's negative, then you should look for another investment. A simple payback is a certain amount of years where you reach to the break-even point, where you have already covered all your expenses and you reached for a balance. The capital recovery factor, which is applied normally to electricity generation, is a measure to evaluate the relation between the cash flow and the investment cost. It is applied to short-term projects using the current dollar for every year. This capital recovery factor is given as annual capital cost divided by the net present value, where the annual capital cost is given as the annuity. Annuity means that the quantity that you are going to get every year from this project minus the net present value divided by the number of years of the project. If this value is 12%, then that would be a recommended value that has been specified by EPRI, which is Electric Power Research Institute of the USA. So far, we did not talk about how the value of money decreases. If we need to do that, then we should consider what's called a discounted cash flow analysis. Now comes to the interest rate, which is a percentage return on investment. That's the percent charged on the sum of money that came based on a loan at the beginning of the project, for example, and it is compounded every year. You may have an evaluation with or without discounting. So evaluation without discounting, time of money is important, but sometimes you might neglect it, especially for term project, as I just mentioned. The net, we've already talked about this issue, sorry. And then there is another factor to consider, which is called minimum attraction rate of return, MARR. It is basically taking care of this reduction in the value of the money, and it normally is concerned with 3 reasons for using it. One of them is the inflation, and another one is related to the kind of risk that's associated with the investment. Are you going with an investment of high risk, especially if you are going to go through an unproven technology, new technology that you don't know whether it will work or not? So a risk factor should be taken into consideration. And would it be wise to spend this cash that you have in this kind of project, or you look for another one? So sometimes you'll find that spending on an energy project is not as profitable as you like to. So and you would rather go to a different kind of investment. This is something for the individuals can be fine, but not for governments, that they have to secure a certain amount of energy flow. The issue of MARR here is coming from this simple example. if you are going to get $1 now or promised $1 next year, then you better take it now because the value decreases. But if we compare with between $1 now and 1.xx next year, so that this xx or this ratio, this fraction is going to take care of these elements that we are talking about, the inflation, the risk, and the return, then this way, yes, it can be. So you say now, I'm going to accept it tomorrow, but I'm going to accept it as, if I'm accepting MARR of 10%, then I can accept 1.1 next year. Then, probably before we conclude today, the issue of identifying what is the present and future values of a single cash flow element can be given by these relations. So we have future value is related to the present value by this. I is the interest rate and N is the number of years. The present value is related by the to the annuity. Annuity is the quantity which is the net cash flow in every year. Or if there are installments on the capital cost, then they have to be accounted for. So the present value based on the annuity is calculated by this relation. Again, I is the interest rate, capital N is the number of years, the span time for the project, and the future value also can be calculated from this relation here. So we're having now talking about present value, P, future value, F, annuity, and the relation between them. And the way that notation is given for these expressions, for example, the expression that we have, the second one, for example, which is P is equal to A into this fraction, is written as P over A with a certain interest rate I for number of years N, and they call it P given A. So we are given the value of A and we calculate P, or P given F, or F given P. So that's the way they are terming this kind of expressions here. An example is given here. Maybe we can use this example to conclude this session, talking about a cash flow that consists of an annuity of $100,000 earned for 10 years at a 7% interest. What's the future value, FA value in this case? Future value relation to the annuity here. So the relation is given in front of us here. F is the future value, A is the annuity, 100,000. I is the interest rate, which is 7%, and N is the number of years. We're talking about a 10 years span of time. Then the future value based on this annuity is given to be this quantity, 1,381,645. And the FA value, the ratio between F and A here is 13.82. Note that in that example, we are considering the values of 100,000 to be constant. So we did not consider the degradation or the decrease in the value of this 100,000 with years. And to do that, there are ways to account for this calculation, which basically are going to take care of present worth. We're going to talk about here. I'll be just browsing through to tell you what is the what is next in this part. It is by just considering this kind of analysis and keeping in mind that the annuity itself or the value is getting less and less every year, and that's something our values that like talk about the present worth, which can be calculated by this formula. And there is also the benefit to cost ratio method, so that you can see whether all of that are done for one reason, just to get an answer, is that project with this information viable for budgeting or not? And then present worth, talking about benefit to cost ratio, and the internal rate of return value. And all of them are different means to calculate the same thing. And now it depends. Normally, PW is considered by both government and private sectors. The B over C, or the benefit over cost, is considered basically in the public sector, whereas the IRR, which is the internal rate of interest, is considered by private industry. So all of them are just meaning the same thing. They are some sort of simple formula that can be considered to, at the end, answer this question. Shall we go ahead with this kind of proposed project or not? Is it worth budgeting or not? As I mentioned, I'm putting a couple of Excel files that give more details into two examples. And it has something like 6 examples in this chapter. 3 of them are just can be solved in 1 or 2 lines. 2 of them, example number 4 and example number 6, are the ones that needs some sort of a substantial calculations for every year over the project lifetime. That's why I put it in Excel file, and I share the Excel files with you in Blackboard. As I said, you are going to get into much more in-depth exposure to this in the economics course of your program. So homework number 1 is already there in Blackboard. That's maybe I can just share this. I can show it to you before you we adjourn this now. I just want to share that Blackboard with us, I mean with you, so that you can have a look at. Yes, go ahead, please.
For the class of today, where can we find the book? I mean, we have now the textbook of the material and the other book, which is thermodynamics. So, which book?
What I covered today, you will be find part of it in the textbook in chapter 6, the start of chapter 6. But chapter 6 does not have this kind of detailed analysis for the power plant, and this you will find it in the thermodynamic book. Let me ask you which chapter you have in the thermodynamic book, because it has changed over the time. Which edition? I'm sorry.
We have the 8th edition.
Oh, actually, I have the 7th, or I was building this over the 7th, which you will find that generally in a chapter which is it's called vapor and combined power cycles. For me here in my version, it is chapter 10. I'm not sure you will find it in your books, either chapters 9 or 10. Okay. And the part of the economic analysis that we have, that we talked about today, you'll find it in chapter 3 of our book, of the course book. Module number 3, the one that we are having today, I'm just opening it. I hope you'll be able to see it. In this module here, we have basically what we have covered today. I added a study guide from the book. This is a summary of the book, talking about the first law of applications. And I'm just emphasizing here that you look at it from page 20 to page 54. This is the one talking about elements of a steady state, steady flow process.
Yeah, which book is this?
This actually is a summary which has been given by the author of the thermodynamics book.
You mean
summarizing chapter, maybe chapter 9 or chapter 10 of your text of your thermodynamics book. It is given some sort of details that are not in our current book. And the presentation is this, which is module 3, session 1. The part on the engineering economic tools that I was just talking about is here. And the IRR calculations, this is an Excel file that has 2 worksheets. Each worksheet is solving one of the examples that are given in the book, but it is given with great details. Going back again here to the part here, we have the homework assignment. I placed it here, which is it's having 3 problems, as I mentioned. And the feedback that I was telling you about as the Google form, please click here and fill that the 3 questions that we have over there.
So, Doctor, our study should be concentrated on these 2 books, the textbook of the course and the thermodynamics approach.
Actually, I would suggest that for the first homework and for the first exam, studying from the thermodynamics book should be enough.
For the first exam.
Yes, for the first homework and for the first test.
Doctor, isn't understanding
About this kind of cycle. Yes?
Doctor, understanding the example you gave today and the last week, would it be enough for the exam?
Understanding means that you are reading it and you are able to solve it by your hand from A to Z.
Yes, okay, exactly.
This is what I mean by understanding. Yes, if this is the case, yes, you should be able with no problem to solve the homework and get through the test.
Okay, good. So we are expecting in the homework and the test and يعني سؤال شامل نفس اللي اليوم في
I have not written the test so far. Will it be like a comprehensive question like that or small components? I have not yet decided that, but basically it's that same principle.
Doctor, would you mind?
It is worth to give it as a whole comprehensive power plant and going through the analysis. That makes more sense. Yes.
Doctor, would you mind to share us with the revision of the thermodynamics books that you have?
I already put it here. I added it today in the morning. Model number, the first thing, study guide for the first law of application. This is the one.
But I thought that's the whole book.
No, this is not the whole book. This is only for the steady state, steady flow part. That's it. Actually, this is taking care of closed system, steady state, steady flow, and a little bit on the uniform state. That's why I said from page 20 to 54 will take care of that, of the elements that we are needing for steady state, steady flow analysis.
So that will be enough for the exam and homework.
This is a summary of this part. Go through this summary and solve problems, like the homework problems.
Well, how about the exam, Doctor?
How about what?
The exam. This will be. I think this is what my friend here is asking. If he goes through this, if we go through this summary.
Yeah, this is what I answered. I mean, you go through the summary, you solve the problems of the homework, and that should make you ready for it.
Ready, Doctor, ready for the exam, which be in 1st of October or?
Yes, it will be 3 or 10th of October, inshallah.
10th, inshallah.
Inshallah.
I believe 10th دكتور would be better لأنه بنكون سلمنا الهومورك وبعدين يعني جانا السولوشن حتى.
Yeah, that's fine. I mean, as I told you, with me it's fine. I just confirm it with Dr. Mahini. I don't think that will be a problem in that.
Inshallah.
Doctor, would you mind uploading the recorded session, please?
Fine. I will send you the link to the recorded sessions, and I thought that you are able to get it yourself.
No.
But not, then I'll share the link with you, and there is a code that you have to give for every session to be able to see it. So I will do that, inshallah.
Okay. يعطيك العافية دكتور.
الله يعافيك. Any further questions?
Yes, can we get also the recording for all the section?
Yeah, this is what I was just mentioning that now I'm going to provide you with the link to the recorded sessions and the code that you need to enter to get them in.
Okay.
Thank you, Doctor.
Doctor, the summary you mean the study guide?
Yes, summary is the study guide, exactly.
Thank you, Doctor.
You're welcome.
Thank you, Doctor.
Thank you. So, yeah, as I mentioned, I'll be available again on Tuesday like we did previous week, inshallah. Otherwise, I'll be reachable through the team, Microsoft Teams.
شكرا لمجهودك، الله يسعدك يا دكتور.
تسلم سيدي العافية.
شكرا يا دكتور، الله يعطيك العافية.
الله يعافيك.
شكرا دكتور، الله يعطيك العافية.
شكرا لك، بالتوفيق إن شاء الله يا شباب.
Doctor, just quick Review, I was going through this summary right now. It's covering only today's session, I believe, which is considering the closed loop and the heat, but it's not covering anything. This is only for module 3, right?
The loop, I'm opening it here, if you are able to see it.
Yes.
Actually, it is going from the very beginning through the closed system, which we're not covering. Or actually, we said that what we need to focus in is basically the open system, and that starts from page 20, if I'm not mistaken. And
yes, until 24 or 54.
19. So here is it. It starts from here, and it is taking the components one by one. First, how to calculate the mass flow rate, how the mass flow rate is related, and then the mass balance, and then the energy balance, and going through the details of the energy balance and what is meant by steady state. So that started from the beginning. And then it's talking about the energy equation here in details. And I think it will give component by component with even some examples are given here, simple ones. So it has, and talking about the components, different components. This is what we did in the previous week. It's not only today's session.
Okay, that's what I was confused.
Examples here for a nozzle alone, give an example maybe for a turbine alone, and so on. So it has more than what we covered today. It actually started early.
Okay, that's I was confused actually. Was it only considered for today's?
No. That's from it's a revision from the beginning.
Yeah, that's what I was confused. I was going through it. I said this is not only today's session.
Yeah, no, it's not only today's, because actually what we did before was a preparation to what we are doing today.
Okay, so that means the exam will cover also all modules 1, 2, and 3.
Actually, 1, 2, and 3 are something. It's like a building block. You are building something. First time we are talking about properties, and then we are talking about processes, and this cycle. The cycle will have properties and processes.
Great, understood. Thank you, Doctor.
You are welcome.
دكتور
تفضل.
الله يعطيك العافيه. ممكن يا دكتور تذكر اختبار كم بيكون سؤال
I cannot hear you بس وضح الصوت شويه معتز لو سمحت.
تسلم لي دكتور. اقول الاختبار يعني نوعيه الاختبار راح يكون مالتيبل تشويسز ولا كيف يا دكتور يعني بالضبط؟
والله دي انا برضو I'm just waiting to hear from Dr. Moheni to what is the recommended type of exam. I'm not inclined for the multiple choice normally, because I prefer the one that we go through an analysis like we did in our example today. I will confirm that and I'll share it with you once we settle on it.
تمام دكتور. بس بيكون اونلاين يعني كيف بنحل يا دكتور بالكيبورد يعني ولا؟
not necessarily. ما هو كيبورد انت لو هتقعد تكتب المعادلات على الكيبورد هنقعد يومين يعني وبالتالي normally what we do is that we can write on a piece of paper وبعد كده نعمل لها scanning.
تمام.
Most probably this is the way. At least I do that with other courses.
ولا how long is دكتور time for الاختبار؟
I would remember that we'll be taking time from the other sessions, so maybe maximum 1.5 hours. Hopefully less. I hope that will be less than that.
Okay, يعطيك العافية.
الله يعافيك. Any further questions يا شباب؟
Thank you, Doctor.
Okay, شكرا يا عبد الإله. في أمان الله.